Okay, so let's dive into logical versus physical database design. You guys already know your way around relational databases. But have you ever thought about how these two levels of design can work together? Or sometimes how they kind of clash? So we're going to be exploring how smart choices at each stage can really improve your database performance, especially when you're working with those large data sets or complex applications.
Yeah, it's interesting. You could think about it like if you have a great recipe, but you're using the wrong ingredients or the wrong cooking methods, the dish might still be edible, but it won't be as good as it could be. So similarly with databases, if you have a mismatch between that logical and physical design, you can run into those performance bottlenecks and headaches later on down the line.
Right. So let's break this down. First, what exactly is logical database design?
So think of it as the blueprint of your data. It defines what entities exist, like those customers or products, how they relate to each other, and what attributes they have, like names or addresses or prices. It's all about ensuring that data integrity, organizing everything logically, and avoiding redundancy. You can use tools like diagrams or UML class diagrams to really help visualize this structure.
Okay, so it's the what's of the data. Then physical design is the how.
Exactly. Physical design is all about the nuts and bolts of how that data is stored and retrieved on the physical hardware. So this includes those decisions about indexes, storage structures, partitioning, and even choosing the right file format for your data. It's all about optimizing that performance and making your database as efficient as possible.
So this is where it gets interesting. Separating these two levels of design, it's super crucial, but I think a lot of people don't fully grasp why.
Yeah, that's true. It gives you a lot more flexibility, and it's really key to that long-term maintainability. Imagine if you need to add a new attribute to an entity in your database. With a well-separated design, you can accommodate that change without redesigning your entire physical storage.
So it's like future-proofing your database, allowing it to adapt to those new requirements without rebuilding from scratch.
Exactly. That's especially important today because things move so fast. That agility is super important. Like if you need to try a new indexing strategy to speed up data retrieval, you can do that without touching your logical data model. This separation is a total game changer, especially with those large, complex databases.
Okay, so we've established that separation is good, but how does each level specifically impact database performance?
So let's start with the logical design. A good logical model reduces data redundancy, which saves storage space and makes updates much faster, since you're not changing the same information in multiple places.
Right, less duplication equals less work for the database.
Exactly. And a good logical design ensures data consistency and integrity, which are super important for any serious application. You can avoid those errors and make your data much more reliable.
That makes sense. And on the physical design side, what are the key performance factors there?
Well, this is where you're thinking about indexing. Indexes are kind of like signposts. They help your database quickly find the data it needs. A smart indexing strategy can really improve query speeds. Think of it like a well-organized library. With a detailed index, you can find the book you need right away, instead of searching every single shelf.
So choosing the right index is really important for that performance.
It is. There's no one perfect solution. You need to understand how you're going to be accessing the data to determine which fields to index. And then beyond just indexing, you've got to choose the right storage structures too. Certain structures work better for certain types of queries. For example, if you frequently perform searches based on a specific date range, you want to store your data in a way that makes those date-based lookups really efficient.
It's like making sure the physical layout of your data matches how you're actually going to use it.
Exactly. And you can't forget about the hardware. Things like using solid-state drives or SSDs for frequently accessed data can give you another performance boost. SSDs are much faster than traditional hard drives, so they can significantly speed up data retrieval.
So it's like fine-tuning the engine of your database to make sure that it runs smoothly and efficiently.
That's a great way to put it.
Now let's flip the script for a second. What happens if we get the design wrong? What are some real-world consequences of a poorly designed database?
Well, one of the most noticeable consequences is slow performance. If your database is slow, users are going to be unhappy. They might even abandon your app.
Especially in India, where speed and efficiency are everything. Nobody wants to be stuck waiting for a slow app.
That's true.
And I imagine poor database performance can also cost you money, right?
Definitely. If your database is inefficient, you might have to spend way more than you need to on hardware. To compensate for those design flaws, you're basically throwing money at the problem instead of addressing the root cause.
And then there's the potential data integrity issues we were talking about earlier.
Yes, if you have a flawed logical design, you might end up with duplicate data or inconsistent data. That can lead to all sorts of problems, from inaccurate reporting to bad business decisions. It's a major headache you really want to avoid.
So what are the key takeaways for people building or managing databases?
The key is that it's not enough to just know SQL. To really master database design, you have to be able to think on both the logical and the physical levels, understand how they work together, how they impact performance, and how to make the best choices at each stage of that design process.
So it's a holistic approach, looking at the big picture,
Yeah.
but also paying attention to the details.
Right. And it's an ongoing process. Your database is never really finished. You're always going to need to be monitoring performance, identifying bottlenecks, and making adjustments as your needs change. It's all about continuous improvement.
It's like any other complex system. You need to constantly adapt and optimize to keep everything running smoothly.
Exactly.
Well, this has been really interesting so far. I feel like I'm learning a lot, and we've only just scratched the surface.
I'm glad you're finding it helpful.
Before we move on, any final thoughts for our listeners?
Yeah, actually, as you're learning about database design, I would really encourage you to look into the concept of normalization. It's a really powerful technique for optimizing that logical design. We don't have time to get into it today, but trust me, it's worth understanding.
Normalization.
Yeah.
Maybe a topic for another deep dive, but for now, I think we've given everyone a lot to think about.
I agree. And, speaking of things to think about, let's talk about when those designs go wrong. What are some warning signs that maybe there's a problem with your database design?
Okay, yeah, let's talk about that. What should we be looking out for?
Well, one of the most obvious signs is slow queries. If your queries are taking forever to run, that's a pretty good sign that something's off. It could be an issue with your indexing or the storage structures you chose. It could even be a poorly designed logical model that's leading to too much data redundancy.
It's like trying to find a needle in a haystack. Or like trying to find a specific grain of sand on a beach. It's there, but finding it is going to take way too long.
Exactly. Another thing to look out for is if it's hard to make changes to your database. If little changes require a lot of work and redoing things, that could mean your design isn't flexible enough. A good database design should be able to adapt to changes pretty easily without having to completely redo everything.
Yeah, it's like if you tried to remodel a house, but all the walls were made of solid concrete. Adapting to new needs would be almost impossible.
Right. And then, of course, there are data anomalies, things like duplicate records, inconsistent data, or even missing values. Those are usually a sign of a problem with the logical design, and they can have serious consequences.
It's like a recipe where the ingredients are all mixed up. So instead of getting a delicious meal, you end up with a disaster.
Yeah, a culinary disaster. These kinds of data anomalies make it hard to trust the data you're working with.
So how can we avoid all of this? What are some best practices to keep in mind for designing databases that work well and can stand the test of time?
Well, the most important thing is to really spend time on requirements analysis. You have to deeply understand what your users need, what kind of data you're going to be storing, and how that data is going to be used. If you rush this part, you're much more likely to end up with design flaws that are hard to fix later.
So it's like laying the foundation before you build a house.
Exactly. Once you really understand the requirements, you can start working on the logical model. This is where you define your entities, their attributes, and how they relate to each other. ER diagrams or UML class diagrams can help you visualize this and make sure everything is consistent.
And this is where normalization comes in, right?
Yes. Normalization is all about optimizing your logical model. It helps you reduce redundancy and ensure data integrity. It can seem a little bit abstract at first, but learning those normalization techniques will really pay off in the long run, especially as your database gets more and more complex.
It's like cleaning up your code to make it more efficient and less likely to have errors.
Yes, exactly. A normalized database is much easier to maintain and less likely to have those data inconsistencies. Once your logical model is done, you can move on to the physical design. This is where you figure out the storage structures, your indexing strategy, and how you'll partition your data. These decisions have a big impact on how well your database performs.
It's like choosing the right tools for a job. Using a screwdriver when you need to work with screws, instead of trying to use a hammer.
You got it. And don't forget to test everything. Once you've implemented your database, really put it through its paces. See how it behaves. Find those bottlenecks. See what could be improved. And make those adjustments. Database design is an iterative process. You're rarely going to get everything perfect the first time around.
It's like fine-tuning a car engine. You need to test it under different conditions to find any potential issues.
Exactly. Great analogy.
Thanks. So we've talked about the importance of good design and what can go wrong with bad design. We've gone over some best practices, but let's face it, not everyone is a database design expert. What advice do you have for someone who's just starting out?
That's a great question. First of all, don't be afraid to experiment. There are so many resources online, articles, tutorials, open source projects. Read them, try things out, learn by doing. There's no substitute for hands-on experience.
It's like learning any new skill. The more you practice, the better you get.
Exactly. And don't be afraid to ask for help. There's a huge community of database professionals out there, online and offline, who are always happy to share what they know, ask questions, join forums, go to meetups. Getting involved in the community is one of the best ways to learn.
Especially here in India, we have a really strong tech community.
Yes, definitely. One last piece of advice I'd give is to stay curious. The world of database design is constantly changing. New technologies and approaches are always coming out, so always be learning. Go to conferences, read industry publications, keep up with the latest trends. That's how you stay relevant and adaptable.
It's like an endless deep dive, always exploring new depths.
I like that. And who knows, maybe someday you'll be the one sharing your database design expertise.
Maybe. Okay, we've covered a lot of ground today, but there's one crucial aspect of database design we haven't talked about yet. Security.
Yes. Security is super important when it comes to databases, especially today. With all the data breaches and cyber attacks happening, you have to protect your data, just like you'd protect your most valuable possessions.
It's like building a fortress around your data.
Exactly. Database security has many layers. It starts with strong authentication to make sure you know who's trying to access your data. Things like strong passwords and multi-factor authentication.
So it's not enough to just build strong walls. You also need good guards at the gate.
Right. Beyond authentication, you also need authorization controls so you can limit what different users can do. Not everyone needs access to everything.
It's like giving different keys to different people, depending on what they're allowed to access.
Exactly. And of course, you need to protect the data itself, both when it's stored and when it's being transmitted. That means encryption, transforming that data so it can't be read without the right key.
It's like scrambling a secret message.
That's it. There are different types of encryption you can use. It depends on your needs and how important security is for you. It's really important to think carefully about your security needs and choose the right encryption methods.
It sounds really complicated.
It can be, but it's absolutely essential. You can't afford to neglect security. The consequences could be devastating.
Definitely. It's a good reminder that database design isn't just about performance and efficiency. It's also about being responsible and protecting that sensitive information.
Well said.
Okay, I think we've given our listeners a lot to think about today.
I agree. We've explored a lot. Logical and physical design, security, best practices.
And we've had some fun with those analogies along the way.
They were good.
Yeah, they really helped me understand some of these concepts.
I'm glad. I always enjoy our deep dives. It's great to explore these complex topics and make them easy for people to understand.
Me too. But before we wrap things up, is there anything else you want to add? Especially for people who are thinking about a career in database design.
Yeah, actually, I want to emphasize how important it is to keep learning. Technology is always changing, and the best database professionals are the ones who are always learning new things and keeping their skills up to date. Don't be complacent. Stay ahead of the curve.
Be a lifelong learner.
Exactly. Read books, go to conferences, take online courses, experiment with new tools. Never stop learning. There are so many opportunities out there for people who are willing to keep growing.
That's great advice. Well, on that note, I think it's time to wrap up this deep dive.
I agree. It's been a pleasure.
For our listeners, thank you for joining us. We hope you found this valuable.
And if you enjoyed it, please like this video, share it with your friends, and subscribe for more deep dives.
Until next time,
Yeah.
happy designing.
You know what's interesting? Database design is becoming more and more connected to other fields.
Oh, yeah. Like what?
We'll take big data analytics, for example. A lot of the tools and techniques they use to analyze all that data rely heavily on database technologies. Knowing how to design and optimize databases for those big data workloads is a really valuable skill these days.
So it's not just about storing and retrieving data anymore. It's about being able to do that complex analysis and find those insights from huge amounts of data.
Right. And then you have machine learning and AI, which are changing so many different industries. A lot of those machine learning algorithms need tons of data to be trained and validated. And a lot of that data is stored in databases.
Yeah.
Knowing how to structure that data and access it efficiently can make a big difference in how well those algorithms perform.
So database design is like a foundation for all these cool new technologies.
Yeah.
They're shaping the future.
Exactly. And as those technologies keep getting more advanced, database designers are going to become even more important. It's a really exciting time to be in this field.
For sure. So let's talk about careers. What's the job market like for someone with database design skills?
The job market is really good, and it's only going to get better. Businesses everywhere need databases, and they need people who can design, implement, and maintain them.
So if you have the right skills, you'll be able to find a job.
Yeah, definitely. And there are a lot of different roles you can choose from. You could be a database administrator, keeping those databases running smoothly, or you could be a database developer, building applications that use databases.
Sounds like there's something for everyone.
There is. You could also get into data warehousing or big data analytics. And with cloud computing becoming so popular, there's a huge demand for cloud database specialists.
So many different areas you could specialize in.
Exactly. And database professionals are paid well, especially if you have specialized skills in those high-demand areas.
Sounds like a pretty good career path.
It can be.
Well, I think we've covered a lot today. Logical and physical database design, security, future trends, career opportunities.
It's been a good overview.
And your analogies were great. They really helped me understand everything.
Glad to hear it.
Before we wrap up, any final thoughts for our listeners?
Just one. Never stop learning. Technology changes so fast. The best database professionals are the ones who are always learning new things.
Be a lifelong learner.
Exactly. Read books, go to conferences, take courses, experiment, get involved in the community. There's always something new to learn.
Great advice. That's all the time we have for today.
It's been fun.
To our listeners, thanks for joining us.
If you enjoyed this deep dive, hit that like button, share it with your friends, and subscribe for more.
Until next time, happy designing. All right, diving right in today, we're tackling conceptual data modeling. You know, that crucial step before you even think about writing database code.
Absolutely. It's like capturing the essence of your data needs, almost like a blueprint before construction.
Okay, blueprint analogy, got it. But for our listeners who are already pretty comfortable with relational databases, how does this help them? Like, how does this level up their game?
Think of it this way. Think of large, complex systems. A clear conceptual model is like your roadmap. It helps you avoid confusion within the team, flags potential issues really early on, and ultimately it just leads to a database that truly fits the purpose.
That makes sense, especially as things get more intricate. So how do we even begin creating this blueprint? Are there certain tools we should be using?
Well, there are two common approaches. One is entity relationship diagrams, or ERDs, and the other one is the unified modeling language, UML. And both of these, they both let us visually represent the core components and how they relate.
Okay, so let's break those down a bit. ERDs and UML. So for folks who are familiar with the databases, but maybe not these specific terms, how do they help capture those real-world data needs?
Think of it this way. You're building an e-commerce platform, maybe something like Flipkart. Your entities are the key players. Customer, product, order, the nouns of your data world.
So entities are like the building blocks, the core things we're tracking.
Yeah, exactly.
How about the relationships between them?
Exactly. Relationships are like the verbs. So a customer places an order contains products, and ERDs and UML, they let us map this out visually. It helps avoid ambiguity and make sure everyone's on the same page.
And attributes, those are the details about each entity.
Precisely. Customer name, product price, order date. It's the specifics that really just flesh out your entities. Both ERDs and UML can handle all of this, but there are some key differences.
Yeah, what are the pros and cons of each? When would someone choose one over the other?
That's a good question. So ERDs are very laser-focused on data modeling. They're simple, they're visual, and they're often preferred for database design specifically. But UML is broader. It can model system behavior, processes, even things beyond just the data.
So for our listeners who are mainly concerned with databases, ERDs might be the go-to.
Often, yes, especially for those starting out.
Yeah.
But regardless of which you choose, simplicity is key.
Right. I've seen some diagrams that are so complex they're more confusing than helpful.
Absolutely. A readable conceptual schema is crucial. Both technical and non-technical folks should be able to understand it. Think of it like a well-organized map. If there's too much detail, you get lost.
Okay, so clarity over complexity. Any tips for actually identifying those entities, relationships, and attributes when we're starting from scratch?
Well, I recommend a methodical approach. First, break down your system into major areas. So for that e-commerce site, it might be order processing, inventory, customer service. And then within each area, you look for those key nouns, those entities. What are the core things we're dealing with?
So it's like kind of reverse engineering the language we use to talk about the system.
Exactly. And once you have your entities, the relationships become clear. Like, how do these things actually interact? And finally, attributes are just the specific details that matter for each entity.
That's super helpful, breaking it down step by step.
Yeah.
I feel like people often just get overwhelmed at this stage.
It's understandable, but having a process makes it much less daunting. And remember, this conceptual model, this is your foundation. A little effort up front saves a ton of headaches later on.
True, like any good construction project.
Exactly.
All right, this is all making a lot more sense now. But to really drive it home, can you walk us through a concrete example, something maybe relevant to our Indian listeners?
Of course. Let's consider a service that I'm sure many of us use daily. A food delivery app like Swiggy or Zomato.
Ooh, I'm hungry already.
So one major area would be order management, right? Within that, we can easily spot entities like customer, restaurant, delivery partner, and of course, the order itself.
Yeah, those are the core players for sure. What about the relationships?
Well, a customer places an order. An order is assigned to a delivery partner, and each order comes from a specific restaurant.
Right. So you see how those verbs naturally connect our entities.
Yeah, it's like we're mapping out the flow of the entire system, but just focusing on the data itself.
Exactly. And then we add those essential details, attributes. For customer, it's customer ID, name, address, phone number, the information that defines a unique customer. For a restaurant, it's restaurant ID, name, cuisine type, location, and so on.
Okay, so it's getting detailed now, but it feels organized. Like each piece has its place.
That's the power of conceptual modeling. Without this, your database can very easily become a tangled mess. And trust me, untangling that mess later is not fun.
Yeah, definitely sounds like something to avoid. So for our listeners, what are the biggest benefits they'll see from investing this time up front?
A robust conceptual model. It leads to a more efficient database, smoother development, fewer errors. It's about clarity, communication, and ultimately a system that truly works. It's almost like a recipe. Getting the ingredients and proportions right from the start ensures a delicious outcome.
I like that analogy. And remember, this is just the beginning. We've laid the groundwork. Next, we'll delve into turning this conceptual model into an actual relational database schema.
Exciting. I'm already curious to see how these entities and relationships translate into tables and columns. But before we jump ahead, any last nuggets of wisdom for our listeners today?
Yeah, don't underestimate the power of simplicity. A clear, concise, conceptual model is worth its weight in gold.
Agreed. And for our listeners, be sure to like, share, and subscribe to The Deep Dive for more deep dives into the world of data. We'll be back soon to continue this journey, so stay tuned.
Welcome back to the deep dive. In part one, we explored those foundations of conceptual data modeling, right? Using tools like ERDs and UML. We learned how to pinpoint those crucial entities, relationships, and attributes, essentially creating that detailed blueprint for our data.
Right. We even used a really relatable example, a food delivery app, to illustrate how to map out a real-world system, something many of our Indian listeners use every day, I'm sure.
Exactly. Now, in part two, we're going to take that blueprint and we're going to transform it into a relational database schema. This is where things get more concrete.
So we're bridging that gap, right, between our conceptual model and the actual structure of our database, like tables, columns, the nuts and bolts of it all.
Precisely. And the good news is this transformation process, it's quite systematic. Each entity in our conceptual model typically translates into a table in our database schema.
Okay, that makes sense. So if we had an entity called customer in our food delivery app, that would just become a customer table.
Exactly. And the attributes of that customer entity, like customer ID, name, address, phone number, those would become the columns of our customer table.
Okay, so entities become tables, attributes become columns.
Yeah.
What about the relationships we mapped out? How did those fit into the schema?
The relationships, they're key here, actually. They determine how those different tables are connected. There are three main types: one-to-one, one-to-many, and many-to-many. Each has a specific way of translating into those table structures.
I remember those types from my database days, but a refresher on how they work in practice would be great.
Of course, of course. Let's start with one-to-one. This means each record in one table relates to only one record in another table. A classic example is a passport table linked to a person table. So each person can have only one passport, and each passport belongs to only one person.
Right, so we could either include those passport details directly in the person table or have a separate passport table linked by a unique ID.
Exactly. Now, one-to-many is actually the most common type. This means that one record in a table can be related to multiple records in another table, but not vice versa. Think of it like a parent-child relationship.
So in our food delivery app, one restaurant can have multiple orders, but each order is linked to only one restaurant.
Precisely. To represent this in our schema, we typically add a foreign key column to the orders table. This foreign key references the primary key of that restaurant table, creating the link.
Got it. The foreign key acts like a bridge, connecting those related records.
A perfect way to put it. Now, many-to-many relationships, those are a bit trickier. This means multiple records in one table can be related to multiple records in another, both ways.
Like in our food delivery app, one order can contain multiple items, and one item can be part of multiple orders.
Exactly. To handle this, we introduce an intermediary table, often called a junction table. In this case, we'd have an order items table with two foreign keys, one referencing the orders table and the other referencing the items table.
So the junction table acts as a go-between, allowing us to track those multiple relationships without duplicating data.
Precisely. Now, as we're mapping out these relationships and structuring our tables, there's a crucial concept to keep in mind: normalization.
Normalization, that rings a bell. It's all about avoiding data duplication, right?
That's a key part of it. Normalization is a set of guidelines that helps us organize data efficiently, minimizing redundancy, preventing those inconsistencies, and making updates much smoother.
So if we need to update a customer's address, we only do it in one place.
Exactly. Normalization helps us create a database that's both space efficient and easy to maintain.
Okay, I see the value in that. But can you give us maybe a concrete example of how normalization might play out in our food delivery app?
Certainly. Let's say initially we designed our orders table to include those customer details like customer name and customer address alongside that order-specific information.
So all the information related to an order is just in one place. Seems convenient. What's the downside?
Well, if the same customer places multiple orders, their name and address would be repeated in each order record. That's redundancy creeping in.
I see. Violating those normalization principles.
Exactly. To fix this, we'd move those customer details to a separate customers table and link it to the orders table using the customer ID as a foreign key.
So we're splitting the data strategically to avoid that duplication. Makes sense.
It does. Not only does this save space, but it also ensures that any update to a customer's information only needs to happen in one place: the customer's table.
It feels like we're bringing order to the chaos, like organizing a messy room.
That's a great analogy. Normalization is all about creating a clean and efficient data structure.
Okay, so we've covered how entities become tables, attributes become columns, and relationships dictate those table connections. We've also touched on normalization as this, guiding principle. What else do we need to consider during this transformation?
Two more crucial aspects are constraints and data types.
Constraints, where we talk about limitations or rules we impose on the data.
Exactly. Constraints are rules that enforce data integrity and prevent those invalid entries. They're like the guardians of our database, ensuring the data stays accurate and reliable.
Okay, could you give some examples of constraints we might use in our food delivery app?
Certainly. One common constraint is not NL. We could apply this to the customer ID column in the orders table, ensuring that every order must be associated with a customer.
So no orders just floating around without a clear owner. Makes sense.
Another important constraint is unique. We might apply this to the phone number column in the customers table to prevent, duplicate accounts with the same phone number.
Right, that's a good way to maintain that accurate customer data and avoid confusion.
Precisely. Constraints are essential for data quality control.
Okay, constraints are the rules. What about data types?
Data types define the kind of values that each column can store. This is crucial for efficient storage and data validation.
So things like text, numbers, dates.
Exactly. For example, the customer name column in our customers table would likely be of type varchar, allowing us to store those text strings. The order date column would be of type date to store date values appropriately.
So by specifying data types, we're kind of telling the database how to handle each piece of information
Yeah.
and validate it.
Precisely. Choosing the right data types, it ensures efficient storage and prevents invalid data from just slipping in.
It sounds like data types act as like a safety net, protecting the accuracy and consistency of our data.
Absolutely. They're fundamental to building a reliable and trustworthy database.
Okay, so we've covered a lot of ground in this transformation process. Entities to tables, attributes to columns, relationships to those table connections, normalization, constraints, and data types.
And remember, this is still just the tip of the iceberg. There's always more to explore in database design.
Well, I feel like we've built a pretty solid understanding of the fundamentals. As our listeners embark on their own database design journeys, what key takeaways should they keep in mind?
I'd say the most important thing is to approach database design systematically. Don't rush into creating those tables and columns without first developing a clear conceptual model. That blueprint is your guide.
Right. A well-defined plan is just essential for success.
Absolutely. And during the transformation process, keep those normalization principles in mind. They'll help you create a database that's efficient and avoids any unnecessary complications.
And don't forget about those constraints and data types, the guardians of our data's integrity and accuracy.
Exactly. By following these guidelines, you can confidently transform your conceptual model into a robust and reliable relational database schema.
So as we wrap up part 2, what exciting territory awaits our listeners in the final part of our deep dive?
In part 3, we'll delve into some advanced techniques for refining your database schema, things like indexing, denormalization, and performance optimization techniques. These are the tools that can really take your database to the next level.
Ooh, advanced techniques. I'm already intrigued. Sounds like we'll be uncovering some pro-level secrets.
We will, so don't miss part 3 of our deep dive into conceptual data modeling. And in the meantime, if you're enjoying this episode, don't forget to like, share, and subscribe to The Deep Dive. We'll see you next time for the grand finale.
Welcome back to The Deep Dive. In parts 1 and 2, we went through that whole world of conceptual data modeling. Right?
Yeah, we really did.
We learned how to kind of, craft that blueprint for our data and then actually turn it into a real relational database schema.
We covered a lot of ground. ERDs, UML, entities, relationships, attributes, normalization, constraints, data types, all those building blocks of a well-structured database.
Right. We laid a solid foundation, but just like, any good architect knows, a strong foundation, it's just the beginning.
Exactly. In this final part, we're going to explore some advanced techniques that can take that database schema from good to great.
Advanced techniques.
Yeah.
All right. Always up for expanding my database toolkit. So what do we have in store today?
Well, today we'll delve into the art of indexing, the strategic use of denormalization, and some powerful performance optimization techniques.
Indexing, denormalization.
Yeah.
These sound like secret weapons for, database masters.
They can be, but like any powerful tool, they require careful consideration and understanding.
Okay, so let's start with indexing. I know indexes can, speed up queries, but how do they actually work their magic?
Imagine searching for a specific book in a massive library without a catalog.
Oh, yeah.
It would be a pretty daunting and time-consuming task.
I can relate to that. The library catalog is a lifesaver.
Exactly. That catalog is like an index for the library. And a database, an index is a data structure that just makes data retrieval much, much faster. It's like a roadmap. It guides the database to the desired records quickly.
So instead of scanning every single row in a table, the database can use the index to, pinpoint those relevant records directly.
Precisely. This can significantly improve the performance of queries, especially when dealing with large tables.
So indexes sound kind of like a must-have then. Are there different types of indexes? How do we choose the right one for the job?
There are various types, each with its own strengths and weaknesses. Some common ones are B-tree indexes, hash indexes, and bitmap indexes.
I vaguely remember those from my database classes, but maybe a refresher on when to use each would be fantastic.
Of course. So B-tree indexes, they're excellent for range queries, like finding all orders placed between certain dates. Hash indexes are incredibly fast for exact matches, like finding a customer by their unique ID.
And what about bitmap indexes? When are those the right choice?
Bitmap indexes are particularly useful for data warehousing scenarios, where you have those low cardinality columns, columns with a limited number of distinct values, like a gender column with values male and female.
So choosing the right index, it really depends on the nature of the data and the types of queries we anticipate, running.
Exactly. And it's important to strike a balance. While indexes do speed up reads, they can slow down writes, because the index needs to be updated every time data changes.
Ah, that makes sense. It's like a trade-off between speed and efficiency.
It is. That's why it's crucial to choose indexes strategically. Focus on the queries that will actually benefit the most from them.
Got it. Indexing is all about finding that sweet spot between read and write performance.
Precisely. Now, let's shift gears a bit. Let's explore denormalization. This technique, it involves intentionally introducing redundancy into our database schema.
Wait, redundancy? Didn't we just go through all that trouble normalizing our data to, eliminate redundancy?
We did, but sometimes a touch of controlled redundancy can actually boost performance.
Interesting. How does that work?
Let's revisit our food delivery app, right? Imagine we have a query that frequently needs to retrieve the restaurant name, along with those order details. If the restaurant name is stored in a separate restaurant's table, we need to perform a join every time we run this query.
And joins can be expensive.
Yeah.
Especially with those large tables.
They can. In this case, we might consider denormalizing the schema by adding a restaurant name column to the orders table, even though it kind of introduces some redundancy.
So we're duplicating the restaurant name to avoid that join operation.
Exactly. This can speed up the query, but it's essential to remember that denormalization, it comes with some trade-offs.
Okay, what kind of trade-offs are we talking about?
Well, as we discussed earlier, redundancy, it can lead to data inconsistencies. If we denormalize, we need to be extra careful to ensure that any updates to that restaurant name are reflected in both the restaurant's table and the orders table.
So denormalization sounds like kind of a double-edged sword.
Mm-hmm.
Powerful, but requires some careful handling.
That's a good way to put it. It's a technique best reserved for specific situations where the performance gains outweigh the risks of that redundancy.
All right, so we've covered indexing and denormalization. What other performance optimization techniques should we add to our arsenal?
Well, there are many, but two essential ones are query optimization and caching.
Query optimization sounds pretty self-explanatory. Is it just about writing better queries?
It can involve that, but it's also about understanding how the database processes queries and using that knowledge to craft queries that execute efficiently.
So things like using the right join types, avoiding unnecessary subqueries, and making the most of those indexes we discussed.
Exactly. Even seemingly small changes to a query, they can have a significant impact on its performance.
And what about caching? How does that help?
Caching is a technique where we store frequently accessed data in memory for, lightning fast retrieval.
So it's like keeping a copy of your favorite book on your bedside table, so you don't have to go to the bookshelf every time you want to read it.
A perfect analogy. By caching frequently used data, we reduce the need to actually access the disk, resulting in much, much faster response times.
Okay, caching seems like a pretty straightforward way to boost performance.
It can be, but it's crucial to choose the right caching strategy and ensure that the cached data stays up to date with any changes in the database.
Right, we don't want to be working with outdated information. That would defeat the whole purpose.
Exactly. Like any performance optimization technique, caching requires careful implementation and monitoring.
Okay, so we've covered an impressive amount of ground in this 3-part deep dive into conceptual data modeling. We started with those basics, learned how to turn our ideas into a schema, and now we've even explored those advanced optimization techniques.
It's been quite a journey. The key takeaway here is that database design, it's an iterative process. It's about finding the right balance between clarity, efficiency, and performance.
Right, there's no one-size-fits-all solution. It's about finding the perfect fit for each specific situation.
Exactly. The best database schema is the one that effectively meets the needs of your application.
As we wrap up this deep dive, what parting words of wisdom do you have for our listeners as they embark on their own database adventures?
I would say approach database design with curiosity and an open mind. Don't be afraid to experiment, learn from your mistakes, and continuously seek ways to improve your skills.
Yeah, and never underestimate the power of a well-defined conceptual model. It's the foundation for a successful and efficient database.
Couldn't agree more. A clear blueprint, it makes that entire development process much smoother, and it helps avoid those, costly rework later on.
Well said. If our listeners have enjoyed this deep dive, be sure to like, share, and subscribe to The Deep Dive for more insightful explorations into the world of technology. Until next time, happy database designing. Welcome back to our deep dive into conceptual data modeling.
It's great to be back.
In our last session, we covered the basics.
And now?
We're ready to jump into some more advanced techniques.
That are essential for anyone working with relational databases.
Especially when you're dealing with large, complex databases.
Something that many of our listeners in India are probably very familiar with.
Exactly.
Yeah.
So let's start with optional relationships.
Okay.
I understand that not every relationship between entities in a database has to be mandatory.
Right.
Kind of like how not all employees might be assigned a company car.
Yeah.
So how do we actually represent this idea of optionality when we're creating a data model?
So in a data model, an optional relationship is usually represented visually by using a small circle or a dashed line at the end of the relationship line that connects two entities.
I see.
So it's a visual cue that tells you that this connection might exist, but it's not a requirement for either entity to exist.
Okay, so it's a way of saying, hey, this relationship is optional.
Yes.
Without having to write it out every time.
Exactly.
I like it.
It makes the diagram much cleaner.
That's pretty clever.
And easier to understand.
Now, what about situations where we have more than two entities involved in a relationship?
That's a good question.
That seems like it could get pretty complex.
It can.
How do we even begin to represent that?
Well, that's where ternary relationships come in.
Okay.
They help us model relationships that involve three entities.
Three entities?
Yes.
Okay, give me an example.
A classic example would be in a project management system where you have employees, you have projects, and you have skills.
Skills. Yeah.
It's not just that an employee has a skill or a project needs a skill, but it's a specific employee with a particular skill being assigned to a particular project.
So it's like a three-way connection instead of just a two-way connection.
Exactly. It's a little more nuanced.
So how do we represent this visually?
Visually, we use a diamond shape to represent the ternary relationship. And then we connect that diamond shape to each of the three entities involved. So you can clearly see that all three entities are playing a role in this relationship.
Okay, so we've talked about how to handle relationships that might not always exist.
Right.
And we've talked about how to handle relationships involving more than two entities.
Yes.
What are some other techniques that we can use to build a more organized and insightful data model?
Well, one very powerful technique is the use of supertypes and subtypes.
Supertypes and subtypes?
Yeah.
Okay, tell me more.
Think of it like creating a family tree within your database.
Interesting.
You might have a supertype called employee with common attributes like name, employee ID, and department. And then you could have subtypes like manager, engineer, or technician that inherit those common attributes from the employee supertype, but also have their own unique characteristics.
So it's kind of like saying all managers are employees, but not all employees are managers.
Exactly.
And this helps to prevent redundancy in our model.
Yes.
And makes it more efficient.
Absolutely.
It's like organizing a massive library.
Yeah.
Having that hierarchy just makes it so much easier to find what you're looking for.
And it makes the model easier to understand and maintain.
Now let's shift gears a bit.
Sure.
And talk about a challenge that often comes up in real-world database design.
Okay.
Different teams, like marketing and engineering, might have totally different views of the same data.
That happens all the time.
Yeah, and this can obviously lead to inconsistencies and conflicts.
It can.
So how do we reconcile these different perspectives?
That's the key.
And create a unified model that everyone can work with?
That's where view integration comes in.
View integration.
Yes.
Okay.
It's a crucial process, especially when multiple stakeholders are involved in the design of a database. Let's imagine for a moment that the marketing team sees a product as a single unit ready for sale. Okay.
While the engineering team views that same product as a collection of individual components.
Interesting.
Both are valid perspectives.
Right.
But their data models might clash if they're not carefully integrated.
Yeah. You can see how that could lead to a lot of confusion and errors down the line.
Absolutely.
So how do we actually go about integrating these different views?
Well, the first step is to carefully compare the different schemas that each team has come up with.
Okay.
Identify any areas where there's a conflict or redundancy.
So it's like playing detective.
Yeah.
Trying to uncover any inconsistencies.
Exactly.
And figure out how to bridge the gaps between those different perspectives.
That's a good way to put it.
Sounds like a delicate process.
It can be.
Are there any specific strategies or techniques that we can use to resolve these conflicts and create that unified, harmonious model?
Absolutely.
Tell me more.
One common approach is to create a new entity that encompasses the shared aspects of those conflicting entities.
Okay.
So going back to our marketing versus engineering scenario,
Yeah.
we might create a new entity called product definition,
Product definition, okay.
which includes attributes that are common to both perspectives, like product name,
Okay.
description, and target market.
Right, so product definition acts as a kind of bridge between those two very distinct views.
Yes.
And establishes a common understanding of what a product actually is.
It helps everyone get on the same page.
What other strategies can we use to integrate those perspectives?
Another strategy is to leverage generalization and specialization,
Okay.
using our supertypes and subtypes that we talked about earlier.
Right, so we can use the family tree concept again.
Exactly.
So in this case, if marketing sees a product as a marketable item with attributes like price and promotional campaign,
Okay.
while engineering sees it as an engineered product with things like manufacturing specifications, we could create a product supertype that includes the common attributes from both of those perspectives.
That's the idea.
And then marketable item and engineered product would become subtypes.
Yeah.
Each inheriting from that product supertype,
Yes.
but also maintaining their own specific attributes.
Exactly.
So we're creating this hierarchical structure
Yeah.
that really reflects the nuances of both perspectives.
It's a way to acknowledge the commonalities,
Yeah.
but also the differences.
This view integration process seems really crucial for building a database that's truly robust and reliable,
It is.
especially when you have multiple teams
Especially when you have multiple teams.
involved in its development.
It can get really messy if you don't do this carefully.
Speaking of managing complexity,
yes.
let's talk about entity clustering,
Okay.
which is a technique that's specifically designed for really massive databases.
Right.
It sounds kind of like a way to organize a gigantic puzzle.
That's a good analogy.
So tell me more.
Well, entity clustering involves grouping related entities and their relationships into clusters.
Okay.
This creates a higher level abstraction of the database. And when you're dealing with large schemas,
Especially in data-rich environments like India,
right.
this technique becomes essential for managing that complexity.
So instead of getting lost in a sea of individual entities and connections,
Right.
we can zoom out and see the bigger picture
Exactly.
by grouping those related elements together.
It's about seeing the forest for the trees.
But how does this actually help us in practice?
Well, think about it this way.
Okay.
If you're dealing with a database for a major transportation network,
Okay.
you might have thousands of stations,
Yeah.
routes,
Okay.
schedules.
Right. It would be overwhelming to try and grasp the entire structure all at once.
It would be.
It'd be like trying to understand a city
Yes.
by looking at a map of every single building.
Too much detail.
Way too much information.
Yeah.
But with entity clustering,
With entity
we could group entities that are related to train schedules together.
Yes.
Entities that are related to passenger information together, and so on.
Right.
This creates a more manageable view.
Yes, exactly.
And it allows us to focus on specific areas of the database without getting bogged down by the sheer volume of information.
It's like breaking down a complex problem into smaller, more manageable chunks.
It's like chapters in a book.
That's a good analogy.
You can dive into a specific section
Yes,
without feeling overwhelmed by the entire text.
exactly.
It seems like entity clustering could also have a pretty big impact on database performance.
It does.
Because if a database has to jump between different areas of storage to find the information it needs to answer a query, it's going to take longer
It will.
to process that query.
It's inefficient.
But by grouping related entities together,
By grouping related entities together.
we're essentially making it easier for the database to access the information it needs.
Right.
And that can really improve performance,
It can.
especially for complex queries.
Especially for complex queries.
So it's about optimizing data access.
It is.
Less searching, faster results.
Yeah.
This is really important in India,
It is.
where we often deal with databases of just enormous scale.
Huge databases.
Those milliseconds saved can really add up when you're dealing with millions of transactions.
They can.
So we've covered some pretty powerful techniques today.
We have.
Optional relationships,
Yes.
ternary relationships,
Uh-huh.
supertypes and subtypes,
Right.
and entity clustering.
It's a good toolkit.
It feels like we've assembled a toolkit
Yes.
for tackling even the most complex data modeling challenges.
I think that's a good way to put it.
But we're not quite done yet. There's still one piece of the puzzle that we need to address,
And what's up?
and that's how to effectively merge those different schemas during view integration.
Ah, yes.
Because view integration is really where all those different perspectives come together.
It is.
And we need to make sure that that process is as smooth and effective as possible.
We do. It's true. View integration can be a little bit tricky. It's not just about identifying those conflicts.
Right.
It's about finding elegant solutions that respect each perspective and ultimately create a unified model that's both accurate and comprehensive.
So it's almost like diplomacy in a way.
It is a bit like diplomacy.
We need to make sure everyone's voice is heard.
Yes.
And that the final data model represents a true consensus.
Exactly. And there are a few different techniques we can use to achieve that. One common approach is to create a new entity that encompasses that common ground between those conflicting entities.
So let's go back to our example of the marketing and engineering teams, each with their own view of a product.
Perfect example. So we might create a new entity called product definition, which includes attributes that are relevant to both perspectives.
So product definition might have attributes like product name, description, and target market.
Exactly.
Information that both marketing and engineering care about.
Precisely. And then we can link this new entity to both the marketing and engineering schemas, creating that bridge between their different views.
It's like we're building a common language that everyone can understand.
It is.
So we can ensure that we're all talking about the same thing.
Absolutely. That's a great analogy. Another strategy is to use generalization and specialization to resolve those conflicts. And this is where our supertypes and subtypes come in handy.
Ah, yes, bringing back that family tree concept.
Exactly. So if two entities have overlapping but distinct attributes, we can create a supertype entity that captures those commonalities and then use subtypes to represent the unique aspects of each perspective.
So if marketing sees a product as a marketable item with attributes like price and promotional campaign, while engineering sees it as an engineered product with manufacturing specifications, we could create a product supertype to represent that core concept of a product.
Precisely. And then marketable item and engineered product would become subtypes, each inheriting from product, but also maintaining their specific attributes.
It's a really clever way to acknowledge both the shared aspects and the unique nuances of each perspective, creating a unified model that's rich and comprehensive.
It's all about finding those connections, building bridges between different viewpoints, and ultimately creating a data model that reflects the complexity and richness of the real world, especially in a country like India where data is so diverse and multifaceted.
Absolutely. Now, we've talked a lot about techniques for organizing and structuring data.
Yes.
But what about the actual impact of these techniques on database performance?
That's a great question.
I imagine that a well-designed data model can make a huge difference.
It can.
Especially when we're talking about large-scale systems.
You're absolutely right. A well-structured data model is essential for optimizing database performance, especially when dealing with the massive data sets that are common in India.
So how does a technique like entity clustering, which we discussed earlier, actually translate into better performance?
So remember how we talked about entity clustering, grouping related entities together? Well, this not only helps us humans understand the database better, but it also makes it easier for the database itself to access and process information.
So it's like organizing a warehouse, putting all the related items together so they're easier to find.
Exactly. When the database needs to retrieve information, it doesn't have to jump all over the place because related data is stored in close proximity.
This makes queries faster and more efficient,
Yes.
which is crucial when you have a system with a large user base and frequent transactions like a railway reservation system or an e-commerce platform.
Precisely those milliseconds saved on each query can add up to significant performance improvements, leading to a smoother user experience and more efficient operations.
It's amazing to see how these seemingly abstract data modeling concepts have such a tangible impact on real-world systems. It really highlights the importance of getting the foundation right.
It does. A well-designed data model is the bedrock of any successful database system, and mastering these advanced techniques can make all the difference, especially when you're working with the scale and complexity of data that we see in India today.
So what would you say to someone who's just starting out on their data modeling journey? What's the most important thing to keep in mind?
I would say, don't be afraid to experiment and explore different approaches. There's no one-size-fits-all solution in data modeling.
It's a field that requires both creativity and rigor.
It's
a blend of art and science.
Exactly. And remember that data modeling is an iterative process. You'll constantly refine and improve your models as you gain more experience and insights.
It's a journey of continuous learning.
It is.
And the more you practice and explore, the better equipped you'll be to tackle even the most complex data challenges.
Absolutely. And as you continue on that journey, remember that there are resources and communities available to support you.
Yeah.
Don't hesitate to reach out to fellow data modelers, share your knowledge, and learn from each other's experiences.
That's a great point. Collaboration and knowledge sharing are essential for growth in any field,
They are.
especially one as dynamic and evolving as data modeling.
Now, we've covered a lot of ground in this deep dive,
Yeah.
exploring the intricacies of optional and ternary relationships, the power of supertypes and subtypes, and the importance of view integration and entity clustering.
We've also seen how these techniques can be applied to create robust, efficient, and insightful data models that can handle the scale and complexity of data in the real world.
But there's one final thought I'd like to leave you with.
I'm intrigued. What is it?
Remember, data modeling isn't just about technical skills. It's also about understanding the real-world context of the data you're working with.
So it's not enough to just know how to create entities and relationships and all those things we've talked about.
No, it's not. You need to understand what that data represents and how it's going to be used in the real world.
Okay, so give me a concrete example of what you mean.
For example, if you're modeling a database for a healthcare system in India, you need to think about things like patient privacy regulations, the diversity of medical practices, and the challenges of data accessibility in rural areas.
So it's about bridging the gap between the technical world of databases and the real-world impact of that information.
Exactly. And that's what makes data modeling such a fascinating and rewarding field. It's right at the intersection of technology, business, and society.
It's about using our technical skills to solve real-world problems and make a positive impact.
Absolutely. And that's something to be excited about.
It is. Well, we've covered a ton of ground in this deep dive, haven't we?
We have.
Exploring all the depths of conceptual data modeling, from optional relationships to ternary connections, supertypes, subtypes, and then all the intricacies of view integration and entity clustering.
It's a lot to take in.
It is, but hopefully it's been valuable for a listener.
I hope so.
We've also seen how these techniques can be applied in a practical way, particularly here in India, where robust and efficient databases are essential for supporting all sorts of operations and driving innovation.
They really are.
So as we wrap up this deep dive, is there one key takeaway you want our listeners to walk away with?
I would say the most important thing is to never stop learning.
Okay.
And exploring the world of data modeling is constantly changing. There's always something new to discover.
So true.
And don't be afraid to challenge yourself. Really push the boundaries of what's possible with data and use your skills to make a real difference in the world.
I love that. Well, thank you so much for joining us on this deep dive.
It's been a pleasure.
And to all our listeners out there, thank you for tuning in, and keep those data models elegant and insightful.
And if you found this deep dive helpful, don't forget to like, share, and subscribe to keep the knowledge flowing.
All right, welcome to another deep dive. You guys know we love to go deep on all things data, and today we're tackling a topic that's crucial for anyone working with databases.
We're talking about turning those ER diagrams, UML models, all those visuals into real working SQL tables.
Exactly. Now, we're assuming you're already familiar with the basics of relational databases, so we're going to skip the 101 and jump right into the tricky stuff.
Think of it as a masterclass, not a beginner's course.
Exactly. So are you ready to dive into the deep end with us?
Absolutely. Let's do it.
Okay, let's start with something simple. You've got an entity in your ER model, something like employee. How does that usually translate into a SQL table?
Well, that's usually pretty straightforward. Your entity in the diagram, it becomes the table name. So you have an employee table, and each attribute, like employee ID, name, address, these all become columns in that table.
Makes sense.
And you choose the right data type for each column, whether it's text, numbers, dates, based on what kind of information it holds.
All right, got to keep things organized. And I bet that primary key we defined in the ER model is important here too, right?
Oh, absolutely. That primary key from your model, that becomes the primary key for the SQL table. It's what makes sure that each row in your table, it represents a unique employee.
Okay, so far so good. But let's spice things up a bit. What happens when you run into one of those many-to-many relationships? Those can get kind of messy fast.
You're telling me. Let's say you're modeling authors and reports, right? Where many authors can contribute to one report and one author can write many reports.
Right, classic example.
You can't really capture that relationship directly in just a single table.
So how do we solve this puzzle then?
We bring in what's called a join table to bridge the gap. So you'd have a table for your authors, a table for reports, and then this third table, the join table, that connects them.
Oh, interesting. So each row in that join table is basically saying, this author worked on this report.
Exactly. That join table, it would have at least two columns. The primary key from the author table and the primary key from the report table, both acting as foreign keys in this new join table.
Ah, so you can easily see who worked on what. That's a neat solution. Now, the source material we're looking at, it also talks about binary, ternary, even n-ary relationships. Can you break down what all of that means in plain English?
Sure. Think of it like the degree of the relationship, a binary relationship. That's the simplest, most common one. It connects two entities, like employee and department.
Right. Two entities. Got it.
Now, ternary, that means we're juggling three entities now. Gets a little trickier. Think of tracking employees, their work locations, and the projects they're assigned to at each location.
Whoa, okay, so now we're dealing with a three-way relationship.
Exactly. And often in SQL, that means you'll need an extra table to properly represent those three entities and how they're linked. And then you've got n-ary relationships, which can involve any number of entities.
Sounds like things can get pretty complex.
Oh, they definitely can. While n-ary relationships can be useful for really intricate scenarios, it's often best, for your sanity, to try and simplify them down to binary or ternary if possible. Easier to manage that way.
Great point. So we've got different relationships figured out. We've talked about how to handle them in SQL. Now let's move on to another concept that's important here. Generalization. What is generalization in the world of database design, and why should our listeners care?
Well, generalization, it's all about showing hierarchies in your data. Think of employee as your broad category, and then you have more specific types of employees under that, like manager, engineer, technician.
Okay, I see the hierarchy, but how does this generalization thing actually translate into SQL tables?
There are a few ways to approach it. One way is to create one giant table for employee. Cram all the attributes for all the different types of employees into that one table.
But wouldn't they create a ton of empty cells if not all employee types share the same attributes? Like an engineer might not have a management level attribute, right?
You're right, that can be an issue. So another way is to create separate tables for each subtype, each table having only the attributes specific to that type of employee.
Okay, so it's like we're breaking down that hierarchy into separate, more focused tables.
Precisely. That can help you avoid having a ton of irrelevant or redundant data in your database. And then there's a sort of hybrid approach where you have the main employee table for the common stuff and then separate tables for the subtypes with their specialized attributes.
So many options. So it sounds like there's no one right way to do this.
Yeah.
It all depends on the specific needs of your database and how you want to structure things.
You got it. And that's the beauty of database design. It's about finding the best solution for your particular situation.
Okay, so we talked about generalization, which is about those easy relationships, right? But the source material also mentions aggregation, which is more about those part of relationships. Could you shed some light on that?
Absolutely. Think about it like this. A software product is made up of a program and a user guide.
Right, classic example.
So the program and the user guide are parts of that whole software product.
Okay, so unlike generalization, where a subtype is a type of the supertype, in aggregation, we have these parts that come together to form a whole.
You got it. And in SQL, you typically represent this by having separate tables for the whole thing and for each of its parts, and then use foreign keys to link them up.
Gotcha. So for our software product example, we'd have a software product table, a program table, and a user guide table, all linked up nicely.
Exactly. And that way you can accurately show that part of relationship within your SQL database.
Okay, this is all starting to click. But before we go any further, I want to make sure I'm getting the big picture here. Are we basically saying that when it comes to translating these complex relationships from our conceptual models into SQL, foreign keys are, like, our best friends?
That's a great way to put it. Foreign keys, they really are essential when you're trying to represent those many-to-many ternary, generalization, and aggregation relationships within SQL. They're the glue that holds it all together.
Okay, I'm glad we clarified that. Now, I know there's a ton more to consider when you're designing SQL tables beyond just mapping the entities and relationships. What other crucial aspects should we be thinking about at this stage?
Well, one thing that often comes up is how to handle situations where you have multiple relationships between the same entities. It can make things really interesting.
Oh, that sounds juicy. I'm dying to hear more about that.
We'll hold on to that thought because, unfortunately, we're out of time for this part of our deep dive.
Don't leave us hanging.
Don't worry, we'll pick up right where we left off in the next part of this deep dive and delve into those multiple relationship scenarios. It's going to be good.
Oh, man, I can't wait. So for all you database nerds out there, make sure you like this part, share it with your colleagues who are struggling with SQL, and subscribe to the channel so you don't miss part 2 of our SQL table design journey. We'll be back soon with more juicy database goodness.
Welcome back to the deep dive. It's great to be continuing this exploration of SQL table design with you.
I'm excited to be back. We left off talking about the challenge of dealing with multiple relationships between the same entities. Can you give us an example of what that might look like in practice?
Sure. Imagine you're building a database for a university. You'd have entities for students, professors, and courses.
Okay, yeah, pretty standard setup.
Now let's think about the relationships. A student can enroll in multiple courses, right?
Yeah, classic many-to-many.
And a professor can teach multiple courses as well.
Another many-to-many.
Yeah.
So far, so good.
But here's where it gets a little more interesting. A professor can also be the advisor for multiple students.
I see where you're going with this.
Yeah.
Now, we have a second relationship between professors and students, but it's a totally different kind of relationship.
You got it. We have one relationship where a professor teaches many students through courses, and another where a professor advises many students. These are distinct relationships, different meanings, potentially different attributes associated with them.
So how do we capture these multiple relationships in our SQL tables without creating a big mess?
That's the challenge, and there are a couple of approaches you can take. One option is to create separate join tables for each relationship.
So we'd have a student course join table for the enrollment relationship and a student advisor join table for the advising relationship.
Exactly. This keeps the relationships clear and distinct. You can even track specific attributes for each relationship that way. For example, the student course join table, it might have a column for the student's grade in that course, while the student advisor join table might have a column for the date when that advising relationship began.
Okay, so each join table is really serving a very specific purpose.
Right. Another option is to combine those relationships into a single join table, but that can get tricky, especially if the relationships have very different attributes.
Yeah, trying to cram everything into one table, I can see how that could become a data nightmare.
You gotta weigh the pros and cons of each approach. A single table might seem simpler initially, but it can lead to more complex queries down the line and potential data redundancy if you're not careful.
So like many things in database design, it's all about finding that balance.
Couldn't have said it better myself. Now, shifting gears a bit, you mentioned earlier that there's a lot more to think about when designing SQL tables beyond just those entities and relationships. What are some other things we should be keeping in mind?
Oh, yeah, for sure. We've really only scratched the surface so far. There's this concept of normalization that I always hear about. But to be honest, it sounds a bit intimidating.
I understand why it might seem that way, but normalization is a really powerful set of guidelines. It helps us create databases that are well-structured, efficient, and reliable.
Okay, I'm listening.
Yeah.
What exactly is normalization?
In simple terms, think of normalization as the art of organizing your data into tables in a way that reduces redundancy, avoids data anomalies. It makes sure that each piece of information is stored in just one place, which makes your database easier to update and maintain.
So it's like tidying up our data and giving everything a proper home.
Perfect analogy. It helps us avoid messy situations where, the same information is scattered across different tables, which can lead to inconsistencies and all sorts of headaches when you try to update or retrieve data.
Yeah, that sounds like a recipe for a disaster. So how does normalization work in practice?
Well, there are these different levels of normalization called normal forms. Each normal form kind of builds on the previous one, adding more rules to ensure data integrity.
So it's like a step-by-step process to make the database structure better.
Precisely. The most commonly used normal forms are first normal form, second normal form, and third normal form. You'll often see those shortened as 1NF, 2NF, and 3NF. Most databases aim for at least 3NF.
Okay, I'm following so far. Can you give us a quick overview of what each of these normal forms is all about?
Sure. 1NF, that's the most basic level. It says that every column in your table should have atomic values, meaning values that can't be broken down into smaller pieces.
So no storing comma-separated lists of things in a single cell. Each piece of information needs its own cell.
Exactly. Now, 2NF, it builds on 1NF by making sure that all the non-key columns are fully dependent on the entire primary key, not just part of it.
I'm not sure I get that one. Can you illustrate it with an example?
Let's say you have a table called orders with columns for order ID, customer name, and order date. The customer name, it depends on the customer ID, but not on the order ID.
Right, because multiple orders can have the same customer.
Exactly. So to satisfy 2NF, you create a separate customers table with columns for customer ID and customer name. And then in the orders table, you'd only keep the order ID, customer ID, and order date.
Ah, that's how you get rid of that redundancy and keep the data nicely organized?
You got it. And then 3NF, that goes one step further. It says that non-key columns should not be dependent on other non-key columns, only on the primary key.
So no sneaky relationships between columns that aren't directly related to the primary key.
You nailed it. By sticking to these normal forms, you create a database that's less prone to errors, easier to update, and often more efficient to query.
Normalization, it's kind of magical. I'm starting to see why it's so important.
It's a fundamental concept in database design, goes hand in hand with this process of transforming conceptual models into those SQL tables.
So by applying normalization right from the design phase, we can make sure our SQL tables are well structured and optimized from the get-go.
You got it. It's about making smart choices that'll make your life easier in the long run.
This has been incredibly insightful, but honestly, I feel like we've only just scratched the surface when it comes to the whole world of SQL table design.
You're absolutely right. There's so much more to discuss, from indexing and query optimization to data integrity constraints and database security.
Sounds like we've got a lot more deep diving to do.
We certainly do. But for now, let's take a break and come back ready to delve into those fascinating topics.
Welcome back to the final part of our deep dive. We've covered so much ground already, from mapping those entities and relationships to that whole normalization thing. But now I really want to get into those more advanced concepts like indexing and query optimization, stuff I've heard about but never fully grasped.
Happy to break it all down for you. Let's start with indexing. Imagine a massive library with millions of books. Without a good catalog system and index, finding a specific book would take forever.
Yeah, you'd be lost in those stacks for days. So is indexing in a database kind of like creating that library catalog?
You got it. It helps your database find the data it needs super quick. It's like this fast-track lookup table, points right to the actual data rows, making searches way more efficient.
So instead of scanning through every single row in a table, the database can use the index to jump right to the good stuff.
Exactly. It's especially helpful for tables with tons of rows or when you're always querying based on certain columns.
Makes sense. But I'm guessing there's a trade-off, right? Creating and maintaining those indexes, it can't be free.
You're sharp. Yeah, indexes take up extra storage space, and they need to be updated whenever the data changes. So it's all about choosing wisely, indexing those columns that are frequently used in your searches.
Right, a balancing act. Now, what about query optimization? What kind of sorcery is involved there?
Think of query optimization as the art of making your database queries run like lightning. It's like finding the most efficient route on a map to get to your destination quicker.
So it's not just about writing SQL that works, it's about writing SQL that works smart.
Precisely. A database management system, it has a query optimizer that analyzes your SQL code and tries to figure out the best way to execute it. But you can help it out by writing queries that are already efficient.
Okay, I'm all ears. Give me some tips to make that optimizer happy.
One big one is being super specific in your where clauses. Instead of grabbing all the data and then filtering it, use precise conditions to fetch only the rows you actually need. Another tip is to use joins carefully. Joining tons of huge tables can be a real drag on performance.
This is all about being mindful of the database's resources and not making it work harder than it needs to.
Exactly. And there's a lot more to it than those basic tips, but it's a good start.
This is great stuff. But before we get too lost in the world of query optimization, let's circle back to a concept we talked about earlier, those data integrity constraints. Remind us what those are and why they're important.
Data integrity constraints are basically rules you set up to keep your data clean and consistent. Think of them as safeguards to prevent bad or inconsistent data from sneaking into your database.
Like having a bouncer at the door, checking IDs, making sure only the right stuff gets in.
Love that analogy. There are different types of constraints. You can have a not NOL constraint to make sure a column can't be empty, or a unique constraint to guarantee that no two rows have the same value in a specific column.
So they're all about maintaining the quality and reliability of the data, making sure we can trust it.
You got it. They're crucial for preventing errors that can ripple through your entire system.
Makes sense. And finally, what about database security? How do we protect all this precious data from those hackers and bad guys?
Database security is a huge topic. Some key things to focus on are user authentication and authorization, making sure people are who they say they are and have the right permissions. And then data encryption, so even if someone gets access, the data is scrambled. And regular security audits are crucial to catch vulnerabilities.
So it's about layers of protection, controlling access, protecting the data itself, and making sure everything's up to snuff.
Exactly. It's about creating a fortress around your database.
Man, this has been quite a journey. We started with those basic building blocks, mapping conceptual models to SQL, and now we're talking about optimization and security, all this advanced stuff. My brain is full.
Glad to hear it. But this is just the tip of the iceberg. There's always more to learn in the world of databases.
So true. But for now, we've given our listeners a great foundation. What are some key takeaways you'd like them to remember from this deep dive?
I think the biggest takeaway is that designing SQL tables that are both robust and efficient takes planning and a solid understanding of those relational database principles.
Well said. And to all our listeners, if you enjoyed this deep dive into SQL, please give us a like, share it with your fellow data enthusiasts, and subscribe to the channel for more deep dives into all things data. Until next time, keep on learning, keep on querying, and keep on diving deep. All right, so welcome back to our deep dive on transforming conceptual data models into SQL.
Yeah, it's great to be back.
Last time we covered the basics, but today we're going deeper. We're taking on weak entities.
Yes, they can be a bit tricky.
They can. They really can. It's like, they always need a +1 to the database party.
That's one way to put it. But yeah, before we get lost in the jargon, maybe we should just step back and make sure everyone understands what we mean by a weak entity.
Right. Back to basics.
So a weak entity, it's an entity in a database that can't, stand on its own.
Relies on someone else.
Exactly. It needs another entity, a strong entity, to exist.
Okay, I think I get that. So let's say we're building a database for an online store. A product would be a strong entity.
Exactly. A product, it has its own unique ID, a name, a description, a price. All those things make it independent.
And then, what about an order item? That's part of an order, right?
You're getting it. That's a perfect example of a weak entity. An order item only makes sense if you know which order it's attached to.
So it's like it can't exist without knowing its parent, the order.
Precisely. And that connection, that dependency is really important when we move from, our conceptual model to the actual SQL tables.
Okay, so how do we show that connection, that dependency in SQL? How do we build that into the database?
Well, that's where primary keys and foreign keys come in.
Those are the building blocks of relational databases, right?
Right. And for weak entities, the primary key is, it's a bit special. It's what we call a composite key.
Composite, meaning it's made up of multiple parts.
Yes. It includes the weak entity's own identifier and also the primary key of the strong entity it depends on.
Okay, so going back to our order item example.
It would have its own item ID, but its primary key would also include the order ID.
I see. So that way it's always tied back to the right order.
Exactly. It creates that unbreakable link, ensuring data integrity.
So it's like the order item is carrying a little piece of its parent order with it everywhere it goes.
That's a fun way to think about it. Now, I know this can get a bit complex, especially when you're dealing with, massive databases and intricate relationships.
Yeah, my brain's already starting to hurt a little.
But don't worry, there are tools that can help us manage this, even automate a lot of it. And they're called case tools, computer-aided software engineering tools.
Case tools, huh?
Yeah.
So they're like the superheroes of database design.
You could say that. They can be real lifesavers, especially when things get complicated. They let you visually model your entities and relationships.
So it's like instead of just writing code, you're drawing a diagram.
Yeah, kinda. But it's more than just a drawing. It's like a blueprint for your database.
Okay, and what else can these case tools do?
Well, once you have that visual model, the best part is they can automatically generate the SQL code for you.
Wait, seriously? So they do the coding for you?
They do. Including all those tricky composite keys we talked about. It saves so much time and reduces the risk of errors.
That's incredible. So even if you're a beginner in SQL, these tools can help you build a robust database.
Exactly. And that's not all. Some case tools can also do this thing called reverse engineering. Imagine you inherit an old database with zero documentation.
Oh no, the dreaded undocumented database.
I know, right? Well, a case tool can analyze that database and create an ER diagram from it.
So it's like it reads the code and then draws you a map of the database structure.
Yep, pretty much. That way you can see how everything is connected and start to understand how it works.
That's amazing. It's like having a translator for old cryptic databases.
Exactly. So yeah, case tools are pretty powerful. They can be a huge help for anyone working with databases.
I'm definitely intrigued. But before we get too deep into all the cool things case tools can do, maybe we should hear some real-world examples of how they've actually been used to solve tricky problems.
Great idea. Let's dive into a few case studies where case tools really made a difference. Okay, so for our first example, let's look at this team. They were building a database for a big university.
Ooh, a university database. That sounds pretty complex. I mean, you've got students and courses and professors and departments. Out there are a ton of relationships to manage there.
Yeah, you're not kidding. And this team, they were really struggling with how to, model student enrollment in courses.
Enrollment, huh? Yeah, that sounds tricky.
At first, they thought about just lumping everything into one giant table, students and enrollments all together.
Oh, I can see how that would be a problem.
Ah.
You'd end up with tons of duplicated data.
Exactly. Imagine having all of a student's information repeated for each course they take. It'd be a nightmare to keep it all consistent.
Yeah, talk about data redundancy. So what did they do? How'd they get around that?
Well, that's where the case tool came in. They used it to model the student and course as separate entities.
Okay, so two separate tables makes sense.
Right. And then the cool thing is they define the relationship between them as a many-to-many relationship.
Many-to-many. I'm not sure I follow.
So think about it. One student can enroll in many courses, right?
Right.
And one course can have many students enrolled in it.
Ah, I see. It's not like a one-to-one thing where each student has only one course.
Exactly. And to represent that many-to-many relationship, they needed something called a junction table.
A junction table. Is that like a separate table altogether?
Yep. The case tool helped them create this separate table just for enrollments. It's often called an enrollment table or registration table. And this table has foreign keys that link it back to both the student table and the course table.
So it's like a bridge between the two, right? Connecting specific students to specific courses.
Exactly. It's like a relationship tracker.
Yeah.
And the beauty of the case tool is it takes care of all the SQL code for creating that junction table, all the constraints, everything.
Wow, so they don't have to write all that code manually.
Nope. The case tool does the heavy lifting, which, really reduces the chance of errors.
That's amazing. So using a case tool, they managed to avoid that whole data redundancy mess and model the relationship accurately.
Exactly. And, it's not just about new databases either. Remember that reverse engineering feature we talked about?
Oh, yeah, where the case tool reads an old database and draws you a diagram.
Right. Well, we've got a great example of that in action, too. This one's about a company that was stuck with a legacy database.
Legacy database, I'm guessing that means it's old, probably messy, maybe not well documented.
You got it. This thing had been cobbled together over years, with different developers adding stuff without much planning.
So it was like a digital hoarder's house, full of stuff, but no one knows where anything is.
That's a great analogy. And the company, they needed to optimize this database, make it run faster, but they couldn't even figure out how it was structured.
Yeah, that's a tough spot to be in. Sounds like a nightmare for any database person.
It was. But luckily, they had a case tool with that reverse engineering capability.
Ah, so they brought in the case tool to decipher this ancient database.
Exactly. They pointed the tool at the database and it analyzed the whole thing, the tables, the columns, the relationships, everything.
And what happened? Did it work?
It did. The case tool managed to create a visual ER diagram from all that messy code.
Wow, that's incredible. So they finally had a map of this digital jungle.
They did. And you know what? Once they could actually see how the database was structured, they were able to spot all sorts of problems. Redundancies, inefficient relationships, even some tables that weren't being used anymore.
It's amazing how a visual representation can make things so much clearer.
Right. And armed with that knowledge, they were able to optimize the database, streamline queries, and actually improve the performance.
So the case tool basically helped them turn this chaotic legacy database into something more manageable and efficient.
Exactly. It's a great example of how case tools can be used not just for building new databases, but also for understanding and improving old ones.
Yeah, that's really impressive. These examples are making me think we need to start using case tools more in our own work.
I know, right? They can be game changers. They make the design process smoother, more efficient, and help us build better databases overall.
Okay, but before we get too carried away with case tools, let's circle back to our main topic, weak entities, and how they fit into the whole database design picture.
Good point. Let's do a quick recap of what we've learned about weak entities and their representation in SQL, and then we can wrap up with some final thoughts.
All right, so let's recap what we've been talking about. We've been on this deep dive into weak entities.
How do you tricky little things?
Right. Those entities in our database that just can't go solo. They always need that strong entity to back them up.
Exactly. They depend on that strong entity for, their very existence.
And we talked about how in SQL, we can represent that link, that dependency, using composite keys.
Right, by including the strong entity's primary key as part of the weak entity's primary key.
Yeah, it's like giving the weak entity a little piece of its parent to carry around.
I like that analogy. And of course, we can't forget about our new best friends, case tools.
Oh, yeah. Those tools are like magic wands for database design. They can do so much to make our lives easier.
They can. From visually modeling those relationships to, generating the SQL code, they really streamline the whole process.
You know what I find really interesting about all this? It's how these concepts, like weak entities and composite keys, they're not just about the technical side of databases.
What do you mean?
Well, they kind of reflect how we think about relationships in the real world, too.
Yeah.
How some things just don't make sense without context.
Oh, I see what you're saying. It's like a leaf on a tree. You wouldn't just have a leaf floating around. It needs to be attached to a branch.
Exactly. Or, think about a team in a company. An individual employee makes more sense when you understand their role within the team, right?
Right, and that connection, that context is what gives meaning to the individual elements.
And when it comes to databases, it's about creating a system that captures not just data points, but also how those data points relate to each other.
Absolutely. It's about building a structure that reflects the complexity of the real world, the interconnectedness of things.
And thinking back to those case tools and those examples we discussed, it's clear that they play a huge role in making sure those relationships are represented accurately.
Definitely. By using case tools, we can enforce those rules, those constraints, and make sure our databases stay consistent and reliable.
Because in the end, it's all about having data that's, trustworthy and meaningful.
Data that we can use to make informed decisions.
So for all our listeners out there, whether you're seasoned database professionals or just starting out, hopefully this deep dive has given you some food for thought.
And maybe even spark some ideas for how to approach your own database designs.
And hey, if you're curious to learn more about weak entities, composite keys, or the awesome power of case tools, we've got some great resources linked in the show notes.
Don't forget to check those out.
And as always, thanks for joining us on this deep dive. If you enjoyed the episode, please like, share, and subscribe to our channel for more insights and discussions on all things data. Until next time. Ready to step up your database game?
Oh, yeah.
Today, we're going deep on database normalization.
All right.
The basics of relational databases already, right?
Right.
But this is about designing them.
Yeah.
Not just to work, but to be elegant and efficient.
Okay.
Imagine a database that's not just functional, but a masterpiece.
Wow.
Where data redundancy is a distant memory.
Yeah, it's so fascinating because normalization helps us create that vision of a database that's robust, reliable, and makes querying a breeze.
Like having a perfectly organized library,
Exactly.
Every book in its place.
Yeah.
You can find anything instantly.
Yeah.
No duplicates.
Absolutely.
So let's break down the goals of normalization.
Okay.
What are we trying to achieve here?
Fundamentally, it's about 3 key things. Eliminating data redundancy.
Okay.
Improving data integrity.
Yeah.
And boosting performance.
Okay, let's start with redundancy. Why is that such a big deal?
Sure.
I get that storing the same information multiple times seems wasteful.
Yeah.
But are there other consequences?
Absolutely. Imagine a company storing customer addresses multiple times for each order.
Okay.
What happens when a customer moves?
Right.
If we don't update every single instance of that address, we end up with inconsistencies and potential errors.
Makes sense.
This can lead to sending mail to the wrong place. Miscommunication, frustration, normalization says, let's store that address just once CE and avoid those headaches.
So it's not just about saving space, it's about reliability.
Exactly.
What about data integrity?
So data integrity is all about ensuring the accuracy and consistency of our data.
Okay.
Normalization enforces rules that prevent anomalies from creeping in.
Right.
For example, it ensures that updates are applied in one central location,
Yeah.
reducing the risk of conflicting information or orphaned records.
So it's like a system of checks and balances for our data.
Precisely. And the best part is, a well-normalized database can often improve performance.
Wait, really?
Yeah.
I thought breaking data into multiple tables would slow things down.
That's a common misconception.
Oh, okay.
While normalization can sometimes lead to more joins when querying,
Right.
it also reduces the amount of data that needs to be scanned and processed overall.
I see.
Think of it like this. Would you rather search for a book in a well-organized library
Okay.
or a cluttered room full of duplicates?
Definitely the organized library.
Exactly.
So we're creating a more efficient system by organizing the data strategically.
Precisely.
But how do we actually achieve this normalization? Where do we even begin?
The heart of the process lies in decomposition.
Okay.
It's about strategically splitting tables into smaller,
Yeah.
more focused ones
Okay.
based on something called functional dependencies.
Okay. Functional dependencies.
Yeah.
That sounds intriguing, but a bit cryptic.
Yeah.
Could you elaborate on that?
Sure. A functional dependency exists when the value of one attribute dictates the value of another.
Okay.
For instance, if we know an employee's ID,
Right.
we automatically know their name.
Yeah.
The employee ID functionally determines the employee name.
So we're looking for those inherent relationships between pieces of information.
Exactly.
It's about understanding which attributes are linked.
Precisely.
Okay.
And that's where the detective work begins.
Right.
Identifying these dependencies requires careful analysis of the data
Yeah.
and understanding the real-world relationships involved.
Right.
It's about understanding the inherent structure of the information.
Like creating a map of how our data is interconnected.
That's a great analogy.
Okay.
And once we've mapped those connections,
Yeah.
we can start to decompose our tables strategically,
Okay.
ensuring that each piece of information has its designated place.
But wouldn't that get complex with large data sets? Are there tools or techniques that can help us visualize these relationships before creating tables?
Absolutely. That's where conceptual modeling comes in.
Right.
Tools like entity relationship diagrams, ER diagrams, help us visualize entities and their relationships before we even touch the database.
So it's like sketching out a blueprint.
Exactly.
Okay.
ER diagrams act as our database blueprints,
Got it.
guiding us toward normalization from the start.
So we're setting ourselves up for success by thinking through the structure.
Precisely.
This is starting to make more sense. But how do we translate these diagrams into practical steps?
Okay.
I've heard of normal forms. Are they part of this journey?
Absolutely. Those normal forms are levels of refinement in our normalization quest.
Okay.
Each form addresses specific types of dependencies,
Yeah.
bringing us closer to that ideal database structure.
Okay. I'm intrigued.
Good.
I'm ready to delve deeper into these normal forms and see how they play out in practice.
Great.
Can we unpack those in the next part of our deep dive?
Absolutely. That's exactly where we're headed next.
Okay, great.
We'll explore the practical implications of each normal form
Sounds good.
and uncover those hidden gems of data organization. Welcome back to our deep dive into database normalization.
Okay, so we've laid the groundwork.
Yeah.
We understand the goals,
Yeah.
right? And the whole idea of functional dependencies.
Yes.
Now let's explore these different levels of refinement.
Okay.
You mentioned normal forms as checkpoints on a map.
Yeah.
So what's our first stop on this journey?
Our first stop is 1NF, first normal form.
Okay.
This is our starting point.
Got it.
1NF is all about ensuring atomicity in our data.
Atomicity.
Yeah.
Sounds like we're getting into particle physics now.
Not quite,
Okay.
but it is a fundamental concept.
Right.
Atomicity in databases means each cell in our table
Yeah.
should hold only a single indivisible value.
Okay.
No more cramming multiple pieces of information into one field.
Got it.
Imagine a database storing phone numbers.
Yeah.
In 1NF, we wouldn't store multiple numbers in one cell separated by commas. Each number gets its own dedicated cell.
So it's like a strict one item per box rule.
Exactly.
Okay.
This seems simple, but violating 1NF can lead to real-world problems.
Right.
Imagine trying to search for a specific phone number
Yeah.
or update one number without affecting others.
Yeah, that sounds like a nightmare.
It becomes a nightmare.
Okay, so 1NF, check.
Yeah.
What's the next level of refinement?
Next up is 2NF,
Okay,
or second normal form.
got it.
2NF builds upon 1NF
Yeah.
and tackles partial dependencies.
Partial dependencies.
Yes.
Now, I'm picturing a data field feeling insecure
Okay.
because it's only partially dependent on something else.
Well, it's not about emotions, but your intuition is spot on.
Okay.
A partial dependency occurs when a non-key attribute depends only on part of the primary key,
Okay.
not the entire key.
Right.
Imagine a table with order details.
Okay.
The order ID and product ID together form the primary key.
Right.
But if the product price only depends on the product ID, not the entire order ID and product ID combination,
Okay.
you have a partial dependency.
So, like saying the price of a banana is determined by the type of banana,
Precisely.
not by which order it's part of.
Exactly.
Yeah.
2NF says every non-key attribute
Yeah.
should depend on the entire primary key,
Right.
not just a piece of it.
Got it.
We would resolve this by moving the product price to a separate table
Okay.
where product ID is the primary key.
That makes sense.
Yeah.
By eliminating these partial dependencies,
Yes.
we ensure that every piece of information in our table truly belongs there.
Right.
And relies on the full identifier.
Exactly.
Okay, 2NF, check.
Okay.
What's next in our normalization journey?
Now we reach 3NF,
Okay,
or third normal form.
right.
This one tackles transitive dependencies.
Transitive dependencies. Sounds
Yeah.
a bit like a grammar lesson.
Why?
What's the data equivalent?
Imagine we have a table storing information about students and their courses.
All right.
It includes student ID, course ID,
Yep.
and the department offering the course.
Okay.
Now, the department depends on the course ID.
Right.
A specific course belongs to a specific department.
Makes sense.
But if we can determine the department solely from the course ID
Okay.
without needing the student ID,
Yeah.
we have a transitive dependency.
So it's like saying we can figure out the department just by knowing the course, regardless of which student is taking it.
Precisely.
We don't need that extra step.
Right. 3NF says, no unnecessary detours.
Got it.
We should remove that transitive dependency
Yeah.
by moving the department information to a separate table,
Okay.
where course ID is the primary key.
Right.
This makes our structure cleaner and more efficient.
Okay, I'm seeing the pattern here.
Good.
Each normal form builds on the previous one,
Yeah.
addressing a specific type of dependency
Right.
and bringing us closer to that ideal structure.
Exactly.
Is there a final level?
There is
Yeah.
a boss level of normalization. It's called BCNF, or Boyce Codd normal form.
BCNF.
It's a stricter version of 3NF
Okay.
and aims to minimize redundancy even further.
Wow. Taking it to the extreme.
You could say that
Yeah.
BCNF ensures that every determinant is a candidate key.
Determinant.
Yeah.
Candidate key.
Yes.
Okay, now you're just showing off.
Sorry, let me simplify.
Look at these.
A determinant is any attribute that determines the value of another attribute.
Right.
A candidate key is any attribute or set of attributes
Yeah.
that could uniquely identify a row in a table.
Yeah.
BCNF ensures that any attribute that determines another attribute is also capable of being a primary key.
So BCNF is like the ultimate normalization champion.
That's one way to put it.
Okay.
But as you progress through your normalization journey,
Yeah.
it's essential to remember that achieving higher normal forms
Right.
doesn't always translate to optimal performance in every situation.
Okay, so there are trade-offs. So normalization isn't just a one-size-fits-all solution.
Right.
Interesting.
While normalization brings numerous benefits,
Yeah.
it can sometimes lead to a higher number of joins when querying data.
Okay.
This can impact performance,
Right.
particularly in scenarios with complex queries
Right.
involving multiple tables.
So it's like having a perfectly organized library
Okay.
where finding a specific book requires checking multiple catalogs
Yeah.
and cross-referencing several indexes,
Right.
efficient in theory,
hmm
but maybe not always in practice.
That's a great analogy.
Okay.
And this is where the concept of denormalization comes into play.
Denormalization.
Yes.
All right, tell me more.
Sometimes strategically introducing a bit of redundancy back into the system
Okay.
can actually boost performance.
Interesting.
It's about finding that sweet spot
Yeah.
between a perfectly normalized structure
Okay.
and practical performance needs.
So it's not just about blindly following the rule.
Exactly.
We need to analyze our specific needs
Yes.
and make informed decisions based on the type of queries we'll be running
Right.
and the performance demands of our application.
Precisely.
Got it.
Database design is an art as much as it's a science.
Okay.
There's no one-size-fits-all solution.
Right.
And achieving the right balance between normalization and performance
Yeah.
is key to building a truly efficient system.
Makes sense.
Let's explore some of these trade-offs
Okay.
and real-world scenarios
Yeah.
in the final part of our deep dive.
All right, so we've been through the land of normal forms.
Yeah.
From atomic values to transitive dependencies.
Mm-hmm.
It's clear that normalization is a powerful tool.
It is.
But I'm really curious about these trade-offs.
Okay.
And this idea of denormalization.
Right.
When does it actually make sense to, deviate from those perfectly normalized structures?
That's where things get really interesting in the real world of database design.
Okay.
It all comes down to context and understanding your specific needs.
Right.
While normalization is generally a good practice. Yeah.
There are times when sticking rigidly to those rules can actually hurt performance.
Okay, give me an example
Sure.
where denormalization might be the better choice.
Imagine you're designing a database for a busy e-commerce website.
Okay.
Customers browsing products,
Yeah.
adding items to their carts,
Mm-hmm.
placing orders.
Right.
Speed is crucial here.
Absolutely.
If every click requires the database to perform multiple joins across several tables,
Yeah.
the user experience will suffer.
I can see how those milliseconds would add up.
Yeah,
Lead to frustrated customers abandoning their carts.
exactly.
So how would denormalization help in this scenario?
Let's say we have a normalized structure where product information, customer details, and order details are stored in separate tables.
Okay.
To display order history, we need to join these tables,
Right.
potentially slowing down the retrieval process.
Like searching for ingredients in different aisles of a supermarket.
Exactly.
Okay.
Denormalization would involve strategically introducing redundancy.
For example, storing some product information directly in the order details table.
Got it.
This avoids a join and speeds up retrieving order history.
So it's like having a mini pantry in your kitchen
Right.
with frequently used ingredients close at hand.
Yeah.
You sacrifice a bit of space and organization,
Mm-hmm.
but you gain convenience and speed.
Precisely.
Oh.
Of course, this introduces some risks.
Right.
If the product information changes.
Yeah.
We need to ensure consistency across both tables.
Makes sense?
But in situations where read performance is paramount,
Yeah.
that trade-off might be worth it.
Fascinating.
Yeah,
So denormalization is a powerful technique,
it is.
but one that needs to be used carefully.
Absolutely.
Are there other scenarios where it might be beneficial?
Definitely. Data warehousing and reporting are prime examples.
Okay.
In these scenarios, we're often dealing with massive data sets and complex analytical queries.
Yeah.
Strict normalization can lead to overly complex queries that take forever to run.
So it's about optimizing for analysis
Yes,
rather than transactional efficiency.
exactly.
We're crunching numbers,
Right.
extracting insights from tons of data,
Precisely.
not worried about updating individual records.
Right.
Okay.
In these cases, we might denormalize to a certain extent
Yeah.
to simplify queries and boost analytical performance.
This has been a great journey.
Yeah.
We've gone from the basics of normalization to the nuances of denormalization
Mm-hmm.
and this balancing act between structure and performance.
It's all about balance.
So what are some key takeaways for our listeners?
Normalization is your friend,
Okay.
but not your dictator.
Right.
Strive for a normalized design,
Yeah.
but don't be afraid to bend the rules when performance demands it.
Good point.
Understand the strengths and weaknesses of each normal form.
Okay.
And remember, those functional dependencies, they're your guide in this data modeling world.
It's not about blindly following rules.
Exactly.
It's about understanding the principles
Yeah.
and applying them strategically
Right.
to create a database that is both elegant and efficient.
Exactly.
Okay.
Database design is an ongoing process.
Right.
As your data grows and your needs change,
Yeah.
don't be afraid to revisit your design.
Okay.
Consider whether further normalization or strategic denormalization is necessary.
This deep dive has been a real eye-opener.
Good.
I feel much more confident in my ability to approach database design with structure and performance in mind.
That's great to hear.
And remember, everyone, this is just the beginning of your journey.
Oh, yeah.
The world of data modeling is vast and always changing.
Absolutely.
There's always something new to learn,
Always.
new techniques to explore.
Exactly.
We hope you found this deep dive into database normalization helpful.
Yeah.
Remember, like, share, and subscribe to the deep dive
Yes.
for more insightful explorations into the world of information.
Absolutely.
Until next time, happy normalizing. Ever try to fit a square peg in a round hole? It's kind of like that when you try to make object-oriented programming and relational databases work together.
Yeah, you get this mismatch.
It's called the impedance mismatch, and that's what we're going to be diving into today.
Exactly.
So for anyone out there who already knows their way around relational databases, get ready.
Yes.
You're about to learn how OOP tries to bridge that gap.
Where it works and where it maybe doesn't work so well.
So it's like two totally different ways of looking at things.
It really is. It's like object-oriented programming, OOP, loves to take data and all the things you do with that data and put it into these packages called objects.
Okay.
But relational databases, they only see tables, rows, and columns. It's like mixing oil and water. They just don't mix easily.
So how does this mismatch actually cause problems for developers? Can you give us some real-world examples?
Sure. Imagine you're building an app to manage land records for villages. In OOP, you might model a land parcel as an object, right?
Yeah.
It'll hold all the details, size, owner, location coordinates, maybe even a history of all the transactions.
Right.
Now, try squeezing all that into a flat database table. It just doesn't fit neatly.
I see what you mean.
You end up splitting it into multiple tables.
Oh, so then your queries become more complex and slower.
Exactly. And that's just one tiny example.
So it's like you're trying to fit a 3D object into a 2D world.
Exactly. You constantly have to translate back and forth, and it can get pretty messy, especially when you add things like inheritance.
Right, inheritance.
That's where one object gets characteristics from its parent object. It's core to OP.
Yeah.
But relational databases, they don't naturally handle that, so developers have to, well, invent workarounds.
It sounds like developers could really use some help with this impedance mismatch.
Thankfully, there is something. It's called Object Relational Mapping, or ORM.
Or RM. So tell me more about ORM. What is it and how does it help?
It's like a bridge.
Okay.
It connects your object-oriented code to your relational database. You get to keep working with your nice, familiar objects, but ORM takes care of all the messy stuff.
Like the conversion to all the tables and columns.
Yes, exactly.
Right.
Like, let's say you have an object for village in your code.
Oh.
ORM lets you define exactly how that village object, its name, population, location, all that stuff gets mapped to columns in your village table in the database.
So I can just stick to my objects and ORM handles the rest.
That's right. And it handles translating queries and updates, too.
Amazing.
You don't have to write as much raw SQL, which, believe me, can be a real pain.
That does sound like a real time saver.
Oh, it is. Tools like Hibernate and Django ORM have been lifesavers for tons of developers.
Yeah, I can imagine. But earlier you said ORM helps to some extent.
Yeah.
Is it not perfect?
Yeah.
What are the downsides?
Well, one thing is that it can slow things down a bit.
Oh, really? How so?
Well, it's doing a lot of work in the background, all that translation.
Okay.
It can impact the speed, especially with complex queries.
I see. So it's a trade-off. Easier for the developer, but possibly slower performance.
Yeah, sometimes. And the ORM tools themselves, well, they can be pretty complex to learn. You really have to understand both OOP and relational databases to use them well.
Okay, it's not just plug and play.
No.
But even though ORM can be helpful, it seems like object relational databases themselves might also offer some solutions.
You're right, they do. They're still relational at their core, but they borrow some ideas from OOP to make them more flexible. It's like they're trying to meet in the middle.
Okay, I'm intrigued. Tell me more about those object-oriented features.
One of the big ones is user-defined functions, UDFs.
Okay.
They let you create custom functions that work on data directly in the database.
Like extending the power of SQL.
Yeah, exactly. You bring some of that OOP power right into your database.
Oh, that's interesting.
Say you need to calculate the distance between two villages using their coordinates. You could code that logic as a UDF.
Right in the database.
Right in the database.
Right.
Then you can use it directly in your SQL queries.
So I keep all the complex calculations close to the data itself.
Exactly. And that often makes things faster because data doesn't have to travel back and forth between the database and your app code.
That makes sense. And what about those abstract data types, the ADTs?
ADTs are another way these databases get more flexible.
Right.
They let you define custom data types, beyond the usual integers and strings that SQL uses.
So instead of using a plain text field for a village's location, I could create a custom type that holds latitude, longitude, and altitude.
You got it. It makes your database much more powerful and able to handle those complex data structures you often find in object-oriented applications.
Right. This is all making a lot of sense. But I think it's time to address the elephant in the room.
You mean the limits of object relational systems?
Exactly. I mean, they borrow some ideas from OOP, but can we really call them object-oriented databases?
Well, that's the big question, isn't it? And honestly, not really.
Really? So even with UDFs and ADTs, there are still fundamental differences.
Yeah, there are. These features help, but object relational databases just don't fully embrace some of those core OOP principles.
Like inheritance and polymorphism that we were talking about earlier.
Those are the big ones. True object-oriented databases handle those seamlessly. Objects inherit properties and behavior from their parent objects and can change their behavior depending on the context.
But with object relational databases, those things are often limited or kind of awkward to implement.
Yeah, it can be like that. It's like adding some spices to a familiar dish. UDFs and ADTs, they add flavor, but they don't change the whole recipe.
So object relational databases give you a taste of OOP, but not the full experience.
That's a good way to put it. Welcome back to part 2 of our deep dive.
It's great to be back. So you left us with a big question at the end of part 1.
Right. Are object relational databases always the best way to go, or could NoSQL be a better choice sometimes?
Yeah, that's a question I've been wrestling with.
It's a tough one. To really understand where NoSQL fits in, we need to go back to that impedance mismatch idea.
Okay, yeah. The difference in how object-oriented systems and relational databases see data.
Right. Now, NoSQL databases often go in a completely different direction.
How so?
They ditch that traditional table and row structure that you find in relational databases.
So no more spreadsheets in the database world. What does that even look like?
Well, it's not just one thing. There are actually many different types of NoSQL databases.
Oh, right. I forgot about that. So each one organizes data in its own way.
Exactly.
Okay, so let's talk about those different types. What are some of the most common ones?
One that's really popular is document databases.
Document databases, okay.
They store data in, documents.
Makes sense.
Often using a format like JSON. It's very flexible, perfect for those complex nested data structures we find in objects.
So instead of forcing my object into a table, I could just store it as a document that mirrors the object structure.
Exactly. It just makes more sense for OOP. It really reduces that impedance mismatch.
Yeah, I can see that. It's a more natural fit.
Right. Say you have an object for a farmer with details about their crops, land ownership, even family members who farm. A document database can hold all that in a single document that looks just like your object structure in your code.
Interesting. So document databases seem like a good fit for object-oriented applications. What other types of NoSQL databases are out there?
Another big one is key value stores. Even simpler in concept.
Okay, simpler. How so?
You have a key, it's a unique identifier, and then a value linked to that key.
Like a dictionary where the word is the key and the definition is the value.
That's the idea. Key value stores are super fast for finding data based on a key.
Right.
People use them for things like caching, session management, or user profiles.
Got it. So document databases, key value stores, any others?
Yep. There are also graph databases.
Well, graph database, okay.
They're all about showing the relationships between data points. Imagine a social network, right?
Okay, yeah.
People connected as friends or followers. That kind of interconnected data makes a graph database a perfect fit.
Wow, it sounds like NoSQL covers a lot of ground. So many options.
It really does. But the choice depends on what your application actually needs, just like choosing between object relational and regular relational databases. The key is knowing the pros and cons of each approach.
That's what makes these deep dives so helpful. But let's get back to whether NoSQL could be a better fit than object relational databases in some cases. What do you think?
Well, one area where NoSQL often shines is scalability.
Scalability, meaning handling tons of data and traffic.
You got it. Many NoSQL databases are designed to be horizontally scalable. It means you can easily add more servers to handle the increasing load.
Okay.
Imagine tracking the supply chain of agricultural products across all of India. That's a massive amount of data, and it's only going to grow. NoSQL can handle that growth smoothly.
I see. Is that something that traditional relational databases, even object relational ones, struggle with?
They can, yeah. Relational databases are usually vertically scalable.
So you add more power to the same server.
Exactly. But there's a limit to how much you can scale that way.
So if your application's going to grow quickly, NoSQL is often the more future-proof choice.
In a lot of cases, yes, especially for web and mobile apps with a ton of users.
Okay, that makes sense. So scalability is one advantage. Are there any other advantages of NoSQL databases?
Another big one is flexibility. Remember that problem of squeezing objects into tables? the whole impedance mismatch issue.
Yeah, how could I forget?
Well, a lot of NoSQL databases are schemaless or have flexible schemas.
Okay.
They make it much easier to adapt as your data requirements change. Let's say you're building an app to connect farmers with buyers, but the data you need to track keeps changing as your app grows. NoSQL handles that gracefully.
It's like it can roll with the punches.
Exactly. You don't have to go through these major migrations or redesigns in your database every time you add a new feature or need to track something new.
NoSQL sounds pretty great so far. Are there any downsides, though? Any trade-offs?
Of course, nothing's perfect. One of the biggest trade-offs is consistency.
Consistency, like making sure everyone sees the same up-to-date data.
That's it. Relational databases are known for their strong consistency guarantees.
Right.
It's because of something called ACD properties.
Okay.
But NoSQL databases, to be so scalable and flexible, sometimes have to relax those consistency guarantees.
So there's a chance that the data might not be perfectly in sync across the system.
It's possible, yeah. It depends on the specific NoSQL database and how it's configured.
I see. So that's something developers need to think carefully about.
Definitely. It's a trade-off, and the right choice depends on your application's specific needs.
Got it. So consistency is one thing to consider. What else should we keep in mind when comparing NoSQL and object relational databases?
Another factor is maturity. Relational databases have been around forever.
Right.
They've been battle-tested in so many critical applications.
Tried and true.
Exactly. NoSQL databases are newer.
Okay.
They're popular, but there's not as much collective experience or established best practices around them yet.
So if you need absolute stability and you want to rely on a lot of existing knowledge, relational databases might still be the safer choice.
It's something to think about. But the NoSQL world is evolving quickly. Lots of companies are using them successfully for even their most critical applications.
It's exciting to see how much the whole world of data management is changing.
It really is. And this whole discussion about NoSQL brings up an interesting point about the impedance mismatch.
Oh, I thought we covered that pretty thoroughly.
We talked about the technical side, the differences between objects and relational data.
Right.
But there's also a conceptual mismatch, one that goes beyond just the tech itself.
Okay, I'm not sure I follow.
Sometimes the way we think about data in an object-oriented way just doesn't naturally translate to the relational way of thinking.
So even with the perfect tools or amazingly flexible databases, we might still run into problems because of how we think about the data.
That's right. It's not just about the tools. It's about understanding these different ways of thinking and finding a way to bridge the gap between them.
Wow, that's a really interesting point. The impedance mismatch isn't just a technical problem, it's a philosophical one.
Exactly. And that's something every developer working with data needs to understand.
So how can developers bridge this conceptual impedance mismatch? Are there any practical things they can do?
That's a great question. And it's one we'll explore in part 3 of our deep dive. We'll look at some specific techniques and approaches to help developers bridge the gap between these two worlds.
Sounds good. I'm ready for part 3. But before we wrap up this part, can we do a quick recap?
Sure. We revisited the impedance mismatch and then took a deep dive into NoSQL databases.
Right. We talked about document databases and key value stores and how they offer a different way to manage data, one that can address some of the challenges of the impedance mismatch.
We saw how NoSQL can be really scalable and flexible, but also that there are trade-offs like data consistency and the fact that the whole NoSQL ecosystem is still relatively new.
And we even went deeper, talking about that conceptual impedance mismatch, which goes beyond the technical differences.
Right. And in part 3, we'll get into the practical stuff.
If you're enjoying this deep dive, don't forget to like and share this episode with your fellow data geeks. And subscribe to the deep dive for more explorations into the amazing world of technology. Welcome back to the deep dive. So in this final part, we're going to get practical. How can developers actually bridge that conceptual impedance mismatch? I'm ready for some real-world strategies.
Okay. One of the most effective things you can do is think about data modeling from both sides right from the beginning.
From both sides, you mean?
Yeah, the object-oriented world and the relational world, right when you're designing.
So I shouldn't design all my objects and then try to figure out how to fit them into the database later.
Exactly. It's better to think about how they might be represented relationally from the very start.
Right.
Like, imagine you're planning a building.
Okay.
If you think about the materials you have and the limitations of the building site from the beginning, you're going to design a much better structure.
Right, that makes sense. So what are some practical steps I can take during the design phase to avoid this mismatch?
One helpful thing is to identify the core entities in your application. Think about how they work as objects, but also how they might fit into relational tables.
Okay, so like if I'm building a system to manage agricultural loans, I might have entities like farmers, loans, crops, and maybe government schemes.
Right. In OOP, those would probably be classes, each with their own properties and methods. But you can also start visualizing how those would look as relational tables.
So farmers would be a table with columns for their name, contact details, land they own, and things like that.
Exactly. And loans could be another table with details about the amount, the interest rate, the repayment schedule.
I'm starting to see it. So by thinking about both representations at the same time, you can spot potential problems early on.
That's the idea. It's like looking ahead for bumps in the road before you even start driving.
Makes sense. So for example, if you have an object with lots of nested properties, you could already start thinking about how to break it down into multiple tables. Or even if a NoSQL database might be a better fit.
That's right. You make those decisions early, and it can save a lot of headaches later. What else? Another helpful thing is to focus on the behavior of your application.
The behavior.
Yeah, how it's actually going to be used, how that translates to how the data will be used. It's not just what the data looks like, but what you're going to do with it.
So thinking about how data will be accessed, updated, and queried, both in my object-oriented code and in the relational database.
You got it. And that's where understanding the strengths of each approach becomes super important.
Okay, I see that. Like if I need to do complex calculations, maybe calculating a farmer's loan eligibility based on a bunch of different factors, I might want to put that logic into a UDF right in the database.
That's a great example. You're thinking about how the data will be used, and you're leveraging the best of both worlds. What about situations where you absolutely need to make sure your data stays consistent?
Yeah, that's super important for things like financial transactions.
Exactly. That's where those ACD properties of relational databases are really valuable.
Right.
If consistency is critical, you might want to stick with a relational database, even if it means a bit more work mapping your objects.
So it's always a balancing act, finding the right mix of flexibility and reliability.
Exactly. There's no one perfect answer. You need to understand the strengths and weaknesses of each approach and choose the right tools for the job. And speaking of tools, we talked a lot about ORM. Does it also help with this conceptual side of the mismatch?
I was wondering that too.
Absolutely. Modern ORM tools give you a lot of control over how objects get mapped to relational data.
So if I have a really complex object, I can use ORM to fine-tune how it's represented in the database.
Yes, and some ORMs can even map objects to NoSQL databases, so the lines are starting to blur between these different approaches.
Wow, that's pretty amazing. But even with all these tools, I guess it still comes down to the developer's understanding, right?
You got it. No tool can replace a developer's ability to think critically about data modeling.
That's what this deep dive has really highlighted for me.
Yeah.
That it's not enough to just use tools. You have to really understand what's going on under the hood.
And that understanding helps you build systems that are not just functional, but also scalable, maintainable, and just plain better. So as we wrap up our deep dive, what are the key takeaways for our listeners?
I think the biggest one is that the impedance mismatch, while a real challenge, can be overcome.
Right. By understanding the differences between object-oriented and relational thinking and using strategies to bridge the gaps, developers can create great systems.
Systems that leverage the best of both paradigms. And I guess the other key takeaway is that there's no magic bullet.
Exactly. The right approach always depends on the specific needs of the application.
Whether it's an object relational database, a NoSQL database, an ORM tool, or some combination of those, the key is to make informed decisions based on a solid understanding of the core concepts.
That's it. Keep learning, keep exploring, and keep pushing the boundaries in this amazing world of data management.
And if you enjoyed this deep dive, please like and share it with your fellow developers. Don't forget to subscribe to the deep dive for more exciting explorations into the world of technology. Until next time. All right, so today we're taking a deep dive into XML and web databases.
Yeah, fascinating stuff.
It really is. And, we use web apps every day.
Right, but how many people think about how they work? Like, how is data organized and used in those apps?
And that's where XML comes in, right?
Exactly, it plays a key role.
So let's unpack this.
Okay, imagine your company has, years and years of data.
About everything.
Right, sales, schedules, like everything.
And they want to use it to make better decisions, obviously.
That's where data warehousing comes in.
So you're not just storing it, but like actually using it to learn stuff.
Exactly. It's not your everyday database for transactions.
Right.
Data warehousing is about looking at the big picture.
Trends, decisions, all that.
Yep. And to do that, you got to organize the data.
Makes sense, but how do you do that with so much information?
One way is something called dimensional modeling.
Dimensional modeling.
Yeah, and specifically something called a star schema.
Okay, I'm listening.
So picture a stall. The center is your fact table.
The fact table.
Right, that's got all your core measurements.
Like sales figures or website traffic.
Exactly, the raw numbers.
Numbers are good, but
they need context.
right, they don't tell the whole story on their own.
And that's where the points of the star come in.
The points.
Yeah, the dimension tables. Those provide the context.
So if I'm looking at, say, sales data.
Your dimension tables could have stuff about the product, the customer, the time, even the location.
So I could see, like, how sales change by region.
Absolutely.
Or time of year or customer demographics.
Exactly. You're slicing and dicing the data.
And it's efficient.
Super efficient with this star schema.
Now, this is where OLA comes in, right?
Online analytical processing, yeah.
I've heard the term, but
not sure exactly what it is.
yeah.
It's basically a set of techniques to analyze that data quickly.
In the data warehouse.
Right, even if it's huge.
So, like, instead of running tons of reports.
You can use OLA to interact with the data directly.
Real-time answers.
Real-time insights.
That sounds powerful, but also kind of overwhelming.
It can be. There are a lot of potential queries you could make.
Right, like with all those products and regions and years of data.
Possibilities explode.
So how do OLAP systems handle all that without slowing down?
Clever techniques,
Like,
view size estimation, and materialized view selection.
okay, so they're basically
Trying to guess what you'll ask and getting a head start.
by pre-calculating some stuff or optimizing how the data is accessed.
You got it.
So they're like anticipating my next move.
In a way, yeah.
Intelligent systems.
They got to be with all that data.
Now, where does XML fit into all this?
XML. That's extensible markup language.
Right, I know the name.
It's a way to represent data in a readable way for both humans and machines.
So it's like a set of rules to create your own markup language.
That's the idea.
So instead of using predefined formats.
You can structure data in a way that makes sense for you.
I see. So XML gives me that flexibility.
Exactly. You define your own tags to represent the data and the relationships within it.
So a well-designed XML can make data easier to understand and use.
For sure.
But what are some key things to think about when designing it? For like data warehousing and web applications.
Well, the schema is super important.
The schema.
Yeah, it's like the blueprint for your XML document.
So it defines what elements you can use.
And the order they go in and how they relate to each other.
So it's about consistency.
Absolutely. No ambiguity.
Like a standardized way to communicate.
Everyone's on the same page.
Makes sense.
Makes the data predictable, which means it's easier to work with.
Gotcha. So good schema is key.
Key to success, yeah.
And we'll talk more about that, right?
Definitely.
After a quick break.
Sounds good.
So we were talking about the importance of a well-designed XML schema.
Right. It's like the foundation.
But are there, like, common mistakes people make when designing them?
Oh, for sure.
Like what?
One big one is not grouping related data together. Say you're working with data about electronic components, right? Like for a circuit board.
Okay.
You've got the component type, the manufacturer, all the specs.
Right.
If that's scattered all over your XML document,
It's going to be a mess.
exactly, hard to work with.
So it's like, if I'm thinking about my circuit board again,
Yeah.
having all the components just jumbled up in a box,
Instead of neatly organized,
right, makes it impossible to find anything.
you want to group related data under a common element.
So like all the resistor information together
Exactly. Then you can access it all as one unit.
makes the document more readable.
And manageable.
So grouping is key.
Definitely.
Any other traps to watch out for?
Another one is promoting data to metadata.
Remoting data.
Yeah, like let's say you have a list of states in your database.
Okay.
Instead of just storing the state names as data.
You might be tempted to create separate elements for each one.
Right, a California element, a New York element.
But that seems like overkill.
It is. It makes your document way too complex.
Like creating a separate drawer for every single component.
When you could just have drawers for category.
Right. Resistors, capacitors, and so on.
Exactly. Got to keep things simple.
So state names are data values,
And should be stored as such.
not turned into metadata.
Right.
So it's a balancing act.
It is.
Grouping data effectively but not overdoing it,
Finding that sweet spot
to make the data easy to work with.
without adding unnecessary complexity.
Makes sense. And this becomes even more important with web applications, right?
And absolutely, because data is constantly moving around.
Between servers and users.
Right.
We use web apps all the time.
But most people don't think about what's happening behind the scenes.
Yeah, like how do databases actually fit into all this?
Right. Imagine you're shopping online, like at an electronics store.
Okay.
You're looking for a specific resistor for your project.
Okay, I'm searching for let's say, a 10K ohm resistor.
Right. So what happens when you hit search?
My browser sends a request to the website server.
Exactly. And that request often uses something called HTTP.
HTTP.
Yeah, Hypertext Transfer Protocol.
Okay, so the server gets my request.
And it has a web application that acts like a middleman.
The middleman.
It figures out how to get you the information you need.
From the database.
Right. And that's where the three-tier architecture comes in.
Ah, the 3 tiers.
Presentation, application, and data.
So the application tier is like the brains.
It translates between the browser and the database.
Using
Often a language called SQL,
Lotus.
structured query language.
Okay, so it sends a SQL query to the database server.
Something like find all 10K ohm resistors.
And the database server finds them.
And sends back the results.
But not just a jumble of data.
No, it sends back structured information.
The specs, the price, the availability.
Maybe even customer reviews.
Okay, and then the application tier takes that information.
And formats it so your browser can understand it.
Using XML or JSON.
Right, and then your browser displays it all nicely.
There's so much going on behind the scenes.
It's a whole symphony of technology.
You also mentioned GetET and POST.
Yeah, those are methods the server can use.
You retrieve information. Can you explain the difference?
Think of GetET like asking a simple question.
Okay.
You're requesting something specific, like a product page.
And the server gives it to you if it exists.
Like asking for a book at the library.
Gotcha. So GetET is for retrieving stuff.
What about pasty?
What about it?
POST is for sending information to the server.
Like submitting a form.
Exactly. You're delivering a message.
With information for the server to process.
Right, like your shipping address.
So GetET is asking, PST is telling.
Good way to remember it.
And both use HTTP.
Right, as the communication protocol.
So every time I click or submit,
your browser and the server are chatting.
using HTTP.
And databases are often involved.
To store and retrieve the information.
Exactly.
And how those databases are designed matters.
Big time. It affects how well everything works.
We talked about XML schemas.
But there's more to it than that. Like what? Well, you got to think about how to handle large objects.
Like images or videos.
Yeah, storing those directly in the database can be inefficient.
So you store them separately and just reference them.
Exactly. Keeps things organized.
And then there's query optimization.
Super important.
Making sure those queries run quickly.
Especially with millions of records.
It's like finding the best route on a map.
Avoiding detours.
All right. No wasted time.
There are techniques for that, like using indexes.
Indexes.
Yeah, and caching data in memory.
So a lot to think about.
Definitely, designing and managing web databases is complex.
But we're starting to get a sense of it.
The key considerations.
To make these systems work smoothly.
And efficiently.
Wow. It's amazing to think about all that happening behind the scenes.
Right. And we've only just scratched the surface.
But we've covered a lot of ground.
From data warehousing to XML and web applications.
Yeah. I feel like I have a much better grasp of how these systems work together.
To manage and deliver information on a massive scale.
Exactly. And it's clear that efficient design and optimization are crucial.
Oh, absolutely. Can't skimp on those.
So what's next? What are some of the challenges or trends on the horizon for all this?
Well, one interesting thing is the rise of NoSQL databases.
NoSQL.
Yeah, it's a different approach to data management.
Different from the relational databases we've been talking about.
Right. NoSQL is often better for unstructured data.
Unstructured data.
Like social media posts or sensor data.
Okay.
It gives you more flexibility in how you store and retrieve that kind of data.
And it scales well.
Very well for massive data sets.
So it's like choosing the right tool for the job.
Exactly. Relational databases are great for structured data.
With a well-defined schema.
But NoSQL is better for more free-form data.
And as web applications become more complex
and handle more diverse types of data,
we'll probably see a mix of both being used.
Most likely the best tool for each situation.
It's exciting to think about the possibilities as these technologies advance.
It is. There's so much potential.
But of course, with great power comes great responsibility.
Always.
We're entrusting more and more data to these systems.
So data security and privacy become even more crucial.
And the ethical considerations.
Forget about that. Bold.
It's a good reminder that technology is a tool.
And we need to use it wisely.
Well said. This deep dive has been really eye-opening for me.
I'm glad to hear that.
I hope our listeners feel the same way.
Me too. It's fascinating stuff.
And if you enjoyed learning about XML and web databases,
Be sure to like, share, and subscribe.
to the deep dive for more explorations into the world of data and technology.
And keep diving deep.
Until next time. Welcome back, everyone, to The Deep Dive. We're diving deep into business intelligence today. I know you're familiar with relational databases, so this should be right up your alley. We'll be looking at the differences between OLTP and data warehouses. And then we'll trace the journey of data through the warehouse lifecycle. We'll also explore the elegance of star schema design and then dive into the fascinating world of OLAP and data mining.
Sounds like a plan. Maybe we could start by contrasting the two main systems, OLTP systems and data warehouses, almost like comparing a busy marketplace to a research library.
That's a great comparison. One is all about speed and efficiency, processing those daily transactions, and the other is all about deep analysis. But for someone already familiar with relational databases, what are the differences when it comes to data warehouses?
I think the biggest difference is the overall mindset. With OLTP, it's about speed and efficiency, processing transactions, keeping a business running. But data warehouses have a different purpose. They're designed to unearth those insights that can drive long-term strategy.
So less about capturing every tiny change and more about getting the big picture.
Exactly. And that difference in purpose, that influences everything, from the structure to the size. Think about it. OLTP systems are constantly being updated. So they use normalized schemas to minimize redundancy and to ensure data integrity. Data warehouses, on the other hand, they prioritize analysis and querying. And that's where that star schema comes in. It sacrifices some normalization for faster insights.
Ah, the star schema. I've heard that's a favorite when it comes to data warehousing. But why? I'd love to hear more about that. But first, how does data even get into a data warehouse? What's the journey from operational systems to a warehouse?
Oh, it's quite a journey. It's like taking raw data and refining it into this valuable resource that can be used for analysis. You start with data extraction. That's carefully pulling the raw data from different systems, often in batches.
So like gathering all your ingredients from different places for a complex recipe?
Exactly. And just like with cooking, you can't just throw everything in at once. The next stage is so important, data cleaning. That's where we scrub the data and remove those inconsistencies and errors. It's like quality control. We have to make sure the insights we pull are from reliable information. Imagine our analysis being thrown off because of different meanings of a word like lead, the metal, versus a sales lead.
A data analyst's nightmare. So it's not just about how much data you have, but also the quality of the data.
Absolutely. And once you have clean data, you move on to data transformation. You mold that data into a format that fits the structure of the data warehouse. Make sure all the data is speaking the same language, so to speak.
So every piece of information fits into the data warehouse design.
Precisely. Then the data is loaded into the data warehouse and ready for its big debut in decision-making. But it doesn't end there. To keep those insights up to date, you have data refreshing. That's periodically updating the warehouse with new information from those source systems.
It's like a library that is always getting new books, right?
Yes. And speaking of libraries, you mentioned the star schema earlier. That design is so important for making the data warehouse easy to navigate and query. It's like a bright star with the central fact table surrounded by all those dimension tables.
Okay, I can picture it. But what makes this star shape so important for a data warehouse? I mean, we know normalized schemas are efficient. What's the advantage of a star schema?
Well, think about it this way. Let's say you're analyzing sales. You want to look at a particular product in a specific region over a certain time period. Now you need to connect data points from sales figures, product details, region, and the time period. The star schema makes those connections simple and intuitive. Fewer joins means faster queries, and you have a clear understanding of the data relationships.
Like a roadmap of the data warehouse, guiding you to those insights you need.
Exactly. And that ease of use, it's so essential for quick and efficient analysis. And that brings us to our next topic, OLAP for decision support. But maybe we should save that for part 2. We're running a bit short on time.
You're right. We have covered a lot. From the basics, like the differences between OLTP and data warehouses, to that meticulous data lifecycle and the star schema. I think we've really laid the groundwork for understanding how businesses can unlock the power of their data.
I think so. We've just started to scratch the surface of this, though. There's so much more to explore. In part 2, we'll delve into OLAP and unravel the mysteries of those data mining techniques. If you're enjoying this so far, don't forget to hit that like button and subscribe so you don't miss part 2 of our business intelligence deep dive. Welcome back to our deep dive on business intelligence. When we left off, we were about to explore the power of OLF for decision support. It's like having this powerful lens, to examine your data from different angles.
I'm really interested to hear more about that. I mean, we've talked about all this data in a warehouse, but how does OLAP actually help us understand it all?
You can think of OLP as an interactive toolkit for exploring your data warehouse. Like, it allows you to slice and dice data, drill down into specifics, or roll up to summaries. You can even pivot the data to see it from different perspectives.
So it's like a multi-dimensional spreadsheet, but for huge data sets.
Exactly. Instead of just rows and columns, you can explore trends, see those outliers, and answer complex business questions without getting overwhelmed. Let's say you're looking at sales performance. Well, with OLOP, you can compare sales across different regions, product lines, even time periods.
That sounds really useful for finding those hidden patterns and making data-driven decisions.
It is. And one of the best things about OLP is that it can do what-if analysis. Users can actually modify historical data to see how different scenarios would have played out.
So it's like a time machine for data. You can experiment with different strategies and see how it could have affected things.
Exactly. Imagine testing pricing models, marketing campaigns, even different product launch dates, all using historical data.
That's incredible. What a great tool for planning and risk assessment. But how does it work technically? Like, how does OLP process all that data so quickly?
Well, one of the key factors is the use of materialized views. These are like pre-calculated summaries that are stored in the data warehouse. They're specifically optimized for certain types of queries. Instead of recalculating every time someone has a question, those answers are ready to go.
So it's like a cheat sheet for the most common questions. It makes data retrieval super fast.
Right. And OLP is even smarter than that. It can actually analyze past queries and then automatically create these materialized views. That way, the most commonly used information is always readily available.
It's like having a personal assistant for all your data analysis needs.
Precisely. But even with those views, some queries might need to process a ton of data. And that's where view size estimation comes in. It uses special algorithms to estimate the size of the view before it's created. This prevents the system from creating views that might be too big.
A delicate balancing act, then. Optimizing for speed, but keeping those views manageable.
Yeah. And it really shows how smart OLA systems are. They're constantly refining those processes to make things run smoothly. Speaking of optimization, I'm really curious about data mining techniques. It sounds, almost like a detective novel or something.
It does. Tell me more.
Well, data mining is all about finding those hidden patterns and relationships in your data, things you might not see through normal analysis. It's like having a digital detective on your team, always sifting through data to find those clues.
I love that. Where do you even begin with something like that?
Well, data mining has a whole range of techniques, each one suited for different tasks and types of data. Some of the most common ones include forecasting, text mining, and clustering.
Okay. Let's start with forecasting. That's something everyone can relate to, right? I mean, we're all trying to predict the future in some way.
You're right. Forecasting is such a big part of making decisions, and data mining gives you the tools to make those predictions with more accuracy. Let's say you want to forecast sales. Well, you'd gather all your historical sales data, and the more data, the better.
Just like predicting the weather. The more historical data you have, the better the forecast.
Exactly. Data mining uses really sophisticated algorithms, kind of like those weather models you mentioned, to find patterns and trends in historical data. Some of the popular methods for forecasting include things like time series analysis, regression analysis, even machine learning.
Break those down for me. Like, what is time series analysis all about?
So time series analysis is about understanding how a variable changes over time. If you look at sales data, for example, you might see, peaks during certain seasons or holidays.
So you're looking for those repeating patterns, right? The ones that give us clues about future behavior.
Yeah. By understanding those patterns, you can start making those predictions about sales. Of course, the real world is never perfectly predictable, but time series analysis gives you a good starting point for your forecasts.
It's like saying we can't predict every rain shower, but we can predict the rainy season.
Exactly. Now, regression analysis, it looks at the relationships between a dependent variable and one or more independent variables.
So you're trying to understand how different things can influence the thing you're trying to predict.
Precisely. Let's say you're predicting sales. You might consider things like advertising spend, competitor pricing, maybe even economic indicators. So by understanding how those factors have affected sales in the past, you can use regression analysis to try and predict future sales based on those same factors.
So if you know more advertising usually leads to higher sales, you can use that relationship to make predictions based on your budget.
Right, and then you have machine learning models, which are much more complex but very powerful for forecasting. They basically learn from the data itself. They can find those patterns and relationships that humans they might miss.
Superpowered digital detectives, huh? Constantly learning and making better predictions based on all the data they're given.
Exactly, and the more data they have, the more accurate those predictions can become. Machine learning is really changing the game when it comes to forecasting. We can make predictions about all sorts of things now, from customer churn to stock prices, with greater accuracy than ever.
It's really amazing how we can use those algorithms to make educated guesses about the future. But what about data that isn't so structured and predictable, like text data?
That's where text mining comes in. It focuses on extracting meaning from unstructured text. It can be challenging, but it's also really rewarding. Think about trying to understand customer sentiment from thousands of online reviews. That's where text mining techniques really excel.
So where do you even start with something as vast and unstructured as text?
Well, text mining can use a variety of techniques, everything from something simple like word frequency analysis to those complex natural language processing algorithms. Word frequency analysis basically just counts how often different words appear in a text. It might seem simple, but it can tell you a lot about the topic, the tone, even the author's perspective.
You're looking for those keywords that keep popping up.
Yeah. Imagine you're analyzing customer reviews. And you see a lot of amazing, fantastic, highly recommended, well, you can assume those customers are happy. But if you see disappointed, broken, waste of money, well, that might be a sign that something needs to be addressed.
You can almost take the temperature of public opinion just from the words people use.
Exactly. But to really dig into the meaning behind those words, we need natural language processing, or NLP.
NLP. That sounds complicated.
It is. It combines linguistics, computer science, and artificial intelligence to help computers understand human language. I mean, language is so complex. And it involves analyzing sentence structure, the parts of speech, even extracting things like people, places, and organizations.
So NLP takes it a step further, right? It's not just the words, it's understanding the meaning behind them.
Precisely. That deeper understanding is so important, especially for things like sentiment analysis, topic extraction, even summarizing text.
So you can go beyond, just basic positive or negative feelings. You can actually understand why people feel that way.
Right. Imagine you're a company analyzing customer feedback for a new product. NLP could help you identify the specific features that customers love or the features that frustrate them. Then you can use those insights to make improvements.
That's so interesting. NLP unlocks a whole new level of understanding from text.
It really does. And finally, we have clustering. This technique helps us group similar data points together. It can reveal those patterns and relationships that might not be visible otherwise.
Okay, how does that work? Like if we had all this customer information, demographics, purchases, all that, how would clustering help us make sense of it?
So clustering algorithms look at all those variables and they group together individuals who have similar characteristics. It's like organizing a bookshelf. But instead of grouping by genre, you group by things like author, theme, or even the color of the cover.
Okay. So you're creating these groups, clusters, of people who have something in common.
Yeah, and this can be really valuable for things like customer segmentation. Like a retail company might use clustering and discover that its customer base naturally falls into specific groups. Then they can tailor their marketing and product offerings to those groups.
It's like creating a personalized shopping experience for each group, right?
That's the power of segmentation. And you can use clustering for other things too. You can use it to identify fraudulent transactions, to group similar documents, so much more.
It sounds very versatile, a technique with a ton of uses in different industries.
It is. And as data mining algorithms improve, I think we'll see even more sophisticated applications for clustering in the future.
Welcome back to the Deep Dive. In parts 1 and 2, we've gone over the basics of business intelligence. From those fundamental differences between OLTP and data warehouses, to the power of OLAP and all those intriguing data mining techniques. But now it's time to look ahead. What does the future hold for this dynamic field?
Oh, the future of business intelligence is full of possibilities. One of the most exciting things on the horizon is the rise of artificial intelligence and machine learning. Those technologies were already changing how we analyze data and make decisions.
I feel like AI and machine learning are everywhere these days.
Hmm.
But for someone who works with data every day, what's the real impact of these technologies? How are they changing the game for business intelligence?
Okay, imagine a world where business intelligence systems can see patterns and make predictions, even recommend actions without any human input. That's the potential of AI.
So it's like having this team of super smart analysts working 24/7, crunching numbers and finding insights.
Exactly. AI can automate a lot of the manual tasks that analysts used to do. That frees them up to focus on strategy and more creative work.
Makes things much more efficient.
Yeah.
But can you give me some real-world examples of how AI is being used in business intelligence today?
One area where AI is already having a big impact is in predictive analytics. Those machine learning algorithms can look at historical data and identify patterns that, honestly, humans just might not see. So businesses can make more accurate predictions about, say, customer churn or sales forecasting.
It's kind of like those recommendation algorithms, right? The ones that suggest things you might like based on your past purchases,
Yeah,
but applied to business decisions.
exactly. And those AI-driven predictions, they're so valuable for optimizing operations, finding new opportunities and making better decisions for growth.
Almost like a crystal ball, but powered by data.
You could say that. AI is also changing natural language processing, that NLP we talked about before. AI-powered NLP tools are getting so much better, so businesses can analyze text data like reviews and social media posts with more depth and accuracy.
So AI is almost like giving businesses this new way to understand what people are saying.
Right. Imagine being able to instantly get insights from customer feedback, understand the sentiment, and even identify those emerging trends, all because of AI-powered NLP.
Like those digital detectives, right?
Yeah.
Sifting through mountains of text to find those clues and connections.
Precisely. And there's more. Another exciting thing happening in business intelligence is the rise of data visualization.
Data visualization, right.
Right.
Making data more accessible, more engaging. I've seen some incredible examples of how you can turn data into visuals that tell a story.
And that's the key. Before, people thought of business intelligence as something very technical, all those spreadsheets and reports. But now there's this understanding that we need to present data in a way that anyone can understand, even if they aren't a data expert.
So we're moving beyond just numbers and charts, right? We're
Yeah.
making data into something that people can connect with, and that inspires action.
Exactly. Businesses can use these data visualization tools to create interactive dashboards, infographics, even immersive data experiences, bringing those insights to life.
I can see how that would be so powerful for communicating information to stakeholders, getting teams excited, really driving those data-driven decisions.
It is powerful, and data visualization tools keep getting better and better. We're going to see some really creative and innovative ways to present data in the future.
This has been such an interesting deep dive into the world of business intelligence. We've really gone through it all, from the basic principles to those advanced techniques and even a peek into the future.
It's been a pleasure talking about this with you. It's so clear that business intelligence can help businesses understand their data, find those hidden patterns, and make smart decisions for success.
And as we wrap up this deep dive, don't forget to hit that like button and subscribe to the deep dive for more explorations into data and technology.
We hope you enjoyed this deep dive into business intelligence. Keep those minds engaged, and we'll see you next time on the deep dive.
Okay, so today we're diving into case tools.
Yeah.
You're already pretty familiar with relational databases.
Right.
So we're going to explore how these tools can be like your secret weapon when you're designing them,
Yeah.
especially for systems like IBM DB2.
Okay.
It's like having a super efficient assistant to guide you through the whole process, from like those initial big picture ideas to the very nitty-gritty details.
Yeah, it's really interesting how case tools actually support, all three stages of database design.
Okay.
Conceptual, logical, and physical.
Right.
And it's not just about drawing diagrams, it's really about visualizing that whole structure of your database and spotting issues even before you write a single line of code.
Yeah, it's like having a blueprint before you start building a house.
Exactly.
So let's start with that conceptual design phase. How do case tools help us there?
So think of it like this.
Okay.
You're mapping out the essential elements of your data world,
Mm-hmm.
the entities, their relationships, and the attributes they possess. And, a lot of case tools use visual languages like ERDs or UML to represent these concepts.
Mm-hmm.
They really let you see the big picture and make sure your database structure makes sense from the very beginning.
ERDs and UML.
Right.
I remember those from my database design days. They are so helpful for visualizing how everything connects.
Yeah.
But how do case tools take us from this conceptual model to an actual database structure?
So that's where the logical design phase comes in. Case tools can automatically translate your conceptual model, whether it's an ERD or a UML diagram, into a relational database structure.
Right.
So that means they generate the tables and columns based on your model, which saves you a ton of manual work.
Wow. That sounds like a huge time saver, especially for these complex databases.
Right.
But isn't there a risk of the tool creating a structure that's not optimized?
Yeah.
I mean, we still need to think about things like normalization, right?
Absolutely. Normalization is crucial for data integrity and efficiency. And here's where good case tools really shine.
Okay.
They don't just blindly create tables. They can actually automatically normalize your data model, applying those normal forms you're familiar with, like 3NF and BCNF, to eliminate redundancy and make sure everything's accurate.
So the tool is essentially doing the heavy lifting of normalization for us.
Yeah, you could say that.
That's pretty impressive.
It is.
But I've also heard that sometimes you need to denormalize certain parts of a database for performance reasons.
Right.
Can case tools handle that as well?
They can.
Okay.
A flexible case tool will allow you to selectively denormalize parts of your database while still maintaining that overall data integrity.
Okay.
It gives you that fine-grained control to balance efficiency and accuracy.
That's the kind of flexibility that you need in the real world.
Exactly.
So we've gone from the big picture concept to our logically structured database model.
Right.
What about the actual implementation on a specific system?
Right.
Like, say, IBM DB2. How do case tools help us with that physical design phase?
So this is where case tools can generate those SQL scripts needed to create your database objects within DB2.
Yo.
Think tables, indexes, constraints,
Yeah.
all those essential components.
Right. Yeah.
It's like having the tool write the code for you based on your design.
So instead of manually writing out all of those SQL statements,
Yeah.
the case tool does it for us.
Exactly.
That sounds incredibly efficient.
Yeah, especially for complex databases.
Yeah.
Imagine the time you save and the errors you avoid.
Right.
But, keep in mind that the level of support for physical design, it really varies between different case tools.
That makes sense.
Some might offer basic database object creation, while others provide more advanced features.
So it's not just about picking any case tool.
Yeah.
It's about finding the right one for your needs and the database system that you are using.
Exactly.
But before we jump into choosing a tool,
Okay.
can we dig a bit deeper into how these tools handle normalization and denormalization? I'm curious about the practical aspects.
Yeah, let's do that.
Okay.
So let's say you have a database for an e-commerce platform.
Okay.
In your conceptual model, you might have an entity called customer with attributes like name, address, and order history.
Yes, that's a very common scenario.
Yeah.
So how would a case tool help us normalize this data?
So a case tool would analyze your model,
Okay.
and it would recognize that storing the customer's address repeatedly for each order, it's inefficient and prone to errors.
Right.
So it would then suggest creating separate tables for customers and orders
Okay.
and linking them through a relationship.
Right. So it's essentially applying the principles of normalization to prevent data redundancy and maintain consistency.
Exactly.
But when would we need to denormalize this structure?
So let's say you're frequently querying the database to display customer order history
Okay.
on their profile page. Retrieving data from multiple tables can sometimes slow down this process.
So for performance reasons,
Right.
we might denormalize the data.
Yeah.
And include some order details directly in the
Yeah.
customer's table.
Exactly.
Okay.
A good case tool would let you make this decision consciously and guide you through the process while minimizing the risks associated with denormalization.
Okay. That clarifies things.
Yeah.
So we've seen how case tools can be a powerful ally in the conceptual and logical design phases.
Right.
Even handling those tricky normalization and denormalization decisions.
Uh-huh.
Now, I'm curious about the physical implementation,
Okay.
especially for a system like IBM DB2,
Yeah.
which I know has its own set of unique features.
It does.
So how do case tools tackle those DB2 specific elements?
That's a great point.
Yeah.
Let's delve into that. In the last part, we were talking about DB2.
Yes.
And you're right. It has its own kind of quirks and powerful features. And this is where choosing the right case tool becomes even more critical.
Okay, so let's talk about picking the right case tool.
Yeah.
What are some key things we should be looking for, especially when working with a system like DB2?
So first and foremost, database support is crucial.
Yep.
You really need to make sure the case tool specifically supports DB2 and all of its unique extensions.
Right.
Otherwise, you might end up with these generic SQL scripts that won't work correctly or take advantage of DB2's capabilities.
So compatibility is key.
Yeah.
What about those handy features we touched upon earlier?
Yeah.
Like reverse engineering and round-trip engineering. Are those important too?
Absolutely. So reverse engineering lets you create a model from an existing database.
Okay.
This is invaluable when you're working with legacy systems.
Right.
Or you need to understand the structure of a database that you didn't design.
Mm-hmm.
And then round-trip engineering, on the other hand, it keeps your model and your database synchronized.
Mm-hmm.
Any changes you make in one are reflected in the other,
Okay.
which is super helpful for ongoing maintenance and collaboration.
Those features sound like real time savers, especially for large projects.
Yeah, for sure.
Speaking of collaboration, what about working in teams? Are there case tools that support collaborative design?
Definitely a lot of modern case tools offer features that allow teams to work together seamlessly.
Okay.
You can share models, track changes, and even work on the design concurrently,
Mm-hmm.
which can speed up the process so much and improve communication.
That makes a lot of sense in today's collaborative environments.
Right.
It's all about working smarter, not harder.
Exactly.
Is there anything else that we should be looking for? Any features that might not be as obvious?
I would say don't underestimate the importance of good reporting tools.
Okay.
Being able to easily generate documentation and diagrams from your case tool
Uh-huh.
is crucial for communication both within your team and with stakeholders who might not be as technical.
Right.
Clear documentation also makes maintaining your database much easier in the long run.
Excellent point. So we've got database support, reverse and round-trip engineering, collaboration features, and robust reporting tools. That's quite a checklist.
It is.
Now, you mentioned that some case tools have particularly tight integration with DB2. Can you give us an example of what that looks like in practice?
Sure. Imagine you're designing a database for a data warehousing application on DB2.
Okay.
You want to leverage DB2's multidimensional clustering feature to optimize query performance.
So multidimensional clustering.
Yeah.
It's a powerful feature, but can be tricky to implement manually.
Exactly. But a case tool with tight DB2 integration would understand this feature, and it would allow you to model it visually.
Uh-huh.
It could then generate the specific SQL code needed to implement multidimensional clustering in your DB2 database,
Right.
saving you from writing complex scripts manually.
Wow, that's a concrete example of how the right case tool can make a huge difference.
Right.
Especially when working with a system like DB2, which has these specialized features.
Yeah.
Now, you mentioned earlier that case tools can automate the generation of database schemas and scripts.
Uh-huh.
Can we dig a little deeper into what that means?
Of course. So remember we talked about the logical design phase?
Yes.
Where you map out the structure of your database?
Right.
The output of that phase is often a database schema,
Okay.
a blueprint that defines all the tables, columns, data types, and relationships.
So it's like the architectural plan for our database.
Exactly. But to actually create the database on a system like DB2,
Uh-huh.
you need to translate that schema into a set of SQL scripts.
Right.
These scripts contain the commands that tell DB2 how to build the tables, define the columns, set up the relationships, and so on.
I see. So the schema is the high-level design,
Yeah.
and the scripts are the detailed instructions for the database system.
Precisely. And here's where case tools shine.
Okay.
Instead of manually writing out all those create table statements, defining data types, setting up foreign keys, and so on,
Right.
a good case tool can automatically generate those SQL scripts based on your schema.
That sounds like a massive time saver, especially when you have a database with dozens of tables and hundreds of relationships.
It is, and it also reduces the risk of errors.
Yeah.
Imagine trying to write all those SQL statements by hand.
Yeah.
It's a recipe for typos and inconsistencies.
Definitely not something I'd want to do.
Right.
So the case tool generates these DB2 specific scripts based on our design ensuring accuracy and consistency.
Yes.
But how does this work with DB2's unique features and extensions?
So that's the beauty of a case tool with tight DB2 integration.
Okay.
It doesn't just generate generic SQL.
Huh?
It understands DB2's specific syntax, data types, and even those unique extensions.
Yeah.
So the scripts it produces are tailored for DB2, ready to run without any modifications.
That level of specificity seems incredibly valuable. It's like having a DB2 expert built into the tool itself.
You could say that. It
Yeah.
takes away a lot of the complexity and allows you to focus on the design
Right.
rather than the intricacies of DB2's syntax.
This has been a fantastic deep dive into how case tools support the entire database design process, from conceptualization to implementation.
It has.
We've seen how they handle normalization, denormalization, and even generate those all-important DB2 specific scripts.
Right.
But what about the future of database design? With all these automation features, are we heading towards self-designing databases?
That's a thought-provoking question, and one that's being explored as we speak. Let's discuss that in the final part of our deep dive.
We've talked a lot about how case tools can streamline database design,
Yeah.
especially for a system like DB2.
Right.
But with all this automation, where is this all heading? Are we on the verge of self-designing databases?
That's a fascinating question.
Yeah.
And while we might not have fully self-designing databases just yet, we're definitely seeing a shift towards greater automation and intelligence in the design process.
So what does that future look like? Can you paint a picture for us?
Sure. Imagine a scenario where you can just describe your data needs in plain language.
Okay.
Maybe even through a conversational interface.
Right.
The system then analyzes your requirements, considers various design options, and then automatically generates an optimized database schema, even factoring in DB2's unique capabilities.
That sounds almost like science fiction. But I can see how the advancements we've been discussing are laying the groundwork for that kind of future.
Exactly. We're already seeing case tools integrated with AI and machine learning algorithms. These algorithms can analyze vast amounts of data, identify patterns, and suggest design choices that might not be apparent to a human designer.
So it's not about replacing human expertise. It's about augmenting it with the power of AI.
Precisely. The goal is to free up human designers from tedious tasks,
Okay.
allowing them to focus on the strategic aspects of database design, like data modeling, performance optimization, and security considerations.
That makes a lot of sense. It's about working smarter, not harder.
Right.
But even with all this automation, I imagine there will always be a need for human oversight and decision-making in database design.
Absolutely. Databases are complex systems that interact with real-world applications and user needs. Human judgment and expertise will always be crucial to ensure that the database meets those needs effectively and ethically.
That's a really important point. So it seems the future of database design is a collaborative one.
Yeah.
A partnership between human ingenuity and intelligent tools.
I couldn't agree more. It's an exciting time to be working in this field with so much innovation and potential for creating truly intelligent and efficient data systems.
Well, this has been a fantastic deep dive into the world of case tools and their role in shaping the future of database design.
It has.
I feel like I've gained a much deeper understanding of how these tools can empower us to create better databases, especially when working with a system like DB2.
It's been a pleasure sharing my insights with you.
Thank you.
Remember, choosing the right case tool can be a game changer for your database design process.
Absolutely. If you're listening to this deep dive and feeling inspired to explore the world of case tools, I encourage you to do your research, check out different vendors, and find the tool that best fits your needs.
Right.
And if you found this deep dive helpful, don't forget to hit that like button and share it with your fellow database enthusiasts.
And be sure to subscribe to The Deep Dive for more insightful explorations of fascinating topics.
Until next time, keep learning, keep exploring, and keep diving deep. Welcome to the Deep Dive. Today, we're diving into the world of SQL.
Oh, SQL.
You know, the language that helps us talk to databases.
It's a powerful one for sure.
It is. So where do we even begin with something like this?
Well, let's start with the basics. Like, how do you actually structure a database?
Okay, so like building a foundation.
Exactly. Think of it like constructing a building. You need a solid foundation and a framework before you start adding the fancy stuff.
Got it. So what's our foundation in the world of SQL?
That would be data definition language, or as it's more commonly known, DDL.
DDL. Okay, I've heard of that.
It's all about creating those tables that will hold our data. Think of it as setting up the different rooms in our building.
Okay, so for example, if I wanted to store information about our customers.
Right, you'd create a customers table.
And then how do I organize all the different types of customer information, like their name and address and all that?
That's where columns come in. Each table has these columns, and each column stores a specific type of data. Like for customer names, you'd use a text column. For maybe their customer ID, you'd use a number column, and so on.
So each column has a specific job.
Exactly. It keeps everything organized and makes it easier to work with the data later on.
Makes sense. So how do we actually create these tables and columns using SQL?
We use the create table statement. So for our customers table, we would write create table customers, and then in parentheses, we define the columns.
So it's like drawing up a blueprint for our table.
A perfect analogy.
Hold on.
Inside those parentheses, you'd list the columns, like customer ID, customer name, city, email, and whatever else you need to store.
So that sets up the structure. But how do we get the actual data into those tables, like the names and addresses of our customers?
That's where we shift from defining the structure to actually manipulating the data. We use data manipulation language, or DML, for that.
Okay, so DDL sets up the structure, and DML is how we work with the data within that structure.
Exactly. Think of DML as the tools you use to furnish and decorate those rooms we built with DDL.
Okay, I'm following. So what are some of the key DML statements?
Well, one of the most common is insert.
Insert, like inserting data.
Right. It's used to add new data into a table. So if a new customer signs up, we'd use insert into customers and then specify the values for each column, their name, city, email, and so on.
So every time we get a new customer, we use insert to add their information to the database.
Exactly. And then there's update. This one's for modifying existing data. Let's say a customer moves to a new city. We would use update customers and set the new city value.
So it's like we're renovating our database, keeping everything up to date.
You got it. And then, of course, there might be times when we need to remove data.
Oh, right, like if a customer closes their account.
Exactly. In those cases, we use the delete statement.
So delete is like demolition. We're carefully removing parts of the database.
It is. But we have to be careful with delete because it permanently removes the data. No going back.
Got it. Demolition is serious business in the database world. So we've covered adding, modifying, and removing data. What about retrieving information from the database? That seems pretty important, right?
Absolutely. That's where the select statement comes in. It's the key to unlocking the insights hidden within your data.
Selectee sounds powerful. Can you give me an example of how it works?
Sure. Imagine you want to find all customers who live in Mumbai. You would use select customer name, email from customers, where city, Mumbai.
Oh, wow. So it's like having a search engine specifically for our database.
Mm-hmm.
And the where clause is like setting the filters, right?
Precisely. The where clause lets you specify conditions to filter the data. It's incredibly useful for finding specific information.
This is all starting to click. We've covered how to create tables, add data, change data, remove data, and even find specific data using select.
We've covered a lot of ground. And believe it or not, we've only just scratched the surface.
There's more.
Oh, there's so much more to explore. SQL has tools like views and subqueries that allow for even more powerful and efficient data manipulation.
Views and subqueries, huh? Those sound intriguing.
They are. We'll dive into those in the next part of our deep dive.
I can't wait. But before we move on, I want to remind our listeners to engage with us. If you're enjoying our deep dive into SQL, please like, share, and subscribe to The Deep Dive.
We love hearing from you, and we'll be right back with part 2, where we'll delve deeper into the world of views and subqueries. Stay tuned.
We'll be back. Welcome back to The Deep Dive. So we ended on views and subqueries. Those sound pretty advanced.
Yeah, they're a bit more intricate, you could say.
Intricate. All right, so let's start with views. What exactly are they?
Okay, imagine you have this massive table filled with data.
Okay, I'm imagining.
But you only really need to work with a specific part of it regularly. So instead of writing this complex query every single time, you can create a view.
So it's like a shortcut.
That's a good way to put it. It's like a prepackaged report that shows just the data you need.
Oh, okay, so it's not like it's creating a separate copy of the data.
No, not at all. It's more like a virtual table based on a predefined select query.
So it's like a window into the underlying data.
Exactly. It shows you just what you need to see. Nothing more, nothing less.
That's really helpful, especially if you need to access the same information frequently.
Right. And there are other benefits too. For instance, views can enhance data security.
Security.
Yeah. Let's say you have a team that needs access to some customer data.
Okay.
But you don't want them to see everything, like sensitive information like credit card numbers.
Right, that makes sense.
You can create a view that shows only the necessary data and keeps the sensitive stuff hidden.
So it's like giving them a customized view of the data.
Exactly. They only see what they need to see, which helps protect sensitive information.
That's smart. Are there any other advantages?
Well, views can also help maintain data consistency.
Also.
Well, if you need to update some data that's used in multiple places, you can just update it once in the underlying table, and the view will reflect those changes automatically.
So it's like having a single source of truth for that data.
Precisely. And that can prevent a lot of headaches down the line.
Views are sounding more and more useful. Okay, so what about subqueries? You said those were coming next.
Right, subqueries. They're basically queries within queries.
Okay, that sounds a little mind-boggling.
It might sound confusing at first, but think of it as a mini investigation within a bigger investigation.
A query within a query. Why would you need to do that?
Well, imagine you want to find all the customers who have ordered a specific product.
Okay.
You could use a subquery to first find the product ID for that product, and then use that ID in your main query to find the customers.
So the subquery helps you narrow down the information you need for the main query.
Exactly. It's like a two-step process.
This is getting deep.
It is, but subqueries are incredibly useful when you need to answer those more complex questions that depend on the result of another query.
So they help break down complex logic into smaller, manageable steps.
Exactly. And that makes your SQL code more efficient and easier to understand.
I'm starting to see the power of these more advanced techniques.
They can be really handy once you get the hang of them.
This has been a great deep dive into views and subqueries. It feels like we're really getting into the nuts and bolts of SQL now.
We are. And the more you learn, the more you'll realize how much you can do with this language.
Before we move on, I want to remind our listeners that we appreciate your engagement. If you're finding this deep dive into SQL helpful, please like, share, and subscribe to The Deep Dive.
We love hearing from you. And we'll be right back with part 3, where we'll wrap up our exploration of SQL fundamentals. Stick around.
Welcome back to The Deep Dive. We've covered so much ground, from creating tables and inserting data to using views and subqueries. My SQL toolbox is feeling pretty full.
That's great to hear.
Yeah.
But there's always room for more tools, right?
True. What else do we need to know?
Let's talk about indexes.
Indexes. I've heard the term, but honestly, I'm a little fuzzy on what they actually do.
Well, think about it like this. Imagine trying to find a specific topic in a huge book, but there's no index.
Oh, I'd have to flip through every single page.
Exactly. It would take forever, right?
Not very efficient. So how do indexes work in SQL?
In a similar way, an index in SQL is basically a data structure that helps speed up data retrieval.
Okay, so instead of searching through every row in a table,
The database can use the index to quickly find the specific data you're looking for.
like a roadmap for the database.
A perfect analogy. It makes a huge difference, especially when you're dealing with large tables with millions of rows.
I can imagine. So how do we create these indexes?
We use the create index statement. You specify the table and the column or columns you want to index.
So if we often search for customers based on their city, we might create an index on the city column.
Exactly. You're telling the database, hey, we're going to be searching by city a lot. Make it easy for us.
And the database sets up a special structure for fast lookups based on that column.
Yep. Indexes are a crucial optimization technique, especially for applications where performance is really important.
It's all about making those queries run as quickly as possible.
Right. Nobody wants to wait around for a slow database.
This deep dive into SQL has been amazing. I feel like I've gained a solid understanding of the fundamentals.
That's what we like to hear. But remember, this is just the beginning.
There's always more to learn, right?
Always. The best way to master SQL is to practice. Experiment with different queries, try out new things.
Where's the best place to start practicing?
There are so many resources available online, tons of free tutorials, interactive platforms, and sample databases to play around with.
So it's really accessible for anyone who wants to learn.
Absolutely. SQL might seem intimidating at first, but it's actually a very logical and structured language.
And like you said, the best way to learn is by doing.
Exactly. Don't be afraid to make mistakes. That's part of the learning process.
This has been an incredible deep dive into SQL. I feel much more confident in my ability to work with databases now.
That's fantastic. And remember, we're always here to help you on your SQL journey.
And to our listeners, if you've enjoyed this deep dive into SQL fundamentals, please like, share, and subscribe to The Deep Dive for more in-depth explorations.
We love having you along for the ride. Keep learning, keep exploring, and we'll see you on the next deep dive.
See you next time. Welcome back to The Deep Dive. You know, we're always diving into some fascinating tech topics, and today is no exception. We're going deep into something that's really crucial for anyone working with relational databases, especially if you're dealing with, those massive data sets we all hear about, query optimization.
It's one of those things that can make a world of difference in performance, especially when you're dealing with a ton of data.
Right. You already know how critical it is to retrieve information quickly, and well, query optimization is all about that, isn't it?
Absolutely. It's about making your database work smarter, not harder. You know what's really fascinating about this?
Look at
A database can execute the same query, the same request for information in multiple different ways.
Okay.
Each one has its own sequence of steps, its own little plan, and some are far more efficient than others.
So it's like having different routes to get to the same place.
Exactly, like
Yeah.
using a navigation app to find the fastest way to your destination.
Right. So some routes are smooth and fast, others are, congested and slow.
Perfect analogy. And just like those navigation apps, databases have a way of choosing the best route, the best execution plan for a query. It's called cost-based optimization.
Cost-based. Okay, so how does a database figure out the cost of a plan? I mean, what does that even mean?
Well, it's mostly about I/O operations, reading data from the disk, writing it back. That's often the biggest bottleneck.
The hard drive. That makes sense.
The database estimates how many of these operations each plan needs, and then it picks the one with the lowest estimated cost.
So it's all about minimizing those trips to the hard drive.
Precisely. Like imagine you need a book from a library.
Okay. Yeah.
It's way faster to look it up in the catalog and go straight to the shelf, right?
Makes sense instead of wandering around aimlessly.
Much faster. Now, are there tools that can make those cost estimates even more accurate?
Well, I would imagine so. I mean, what kind of tools are we talking about?
One of the most powerful is an index.
Okay, an index,
Yep.
like at the back of a book.
Exactly. It's a specialized lookup table for a specific column in your database.
So it lets the database find specific rows much faster. You don't have to scan the whole table.
You got it, just like that library catalog.
Right. Tells you exactly where to find the book.
Boom. And just like that, an index cuts down the I/O operations, making queries much faster.
Indexes sound like a pretty big deal. Are there any other techniques that databases use to make those cost estimates really sharp?
Oh, definitely. Many databases use something called histograms.
Histograms, okay.
Think of it like this. A histogram keeps track of how the data values are distributed in a column.
So like how many people are in different age groups if you have an age column?
Exactly. Like a bar chart showing how often different values appear.
Okay, now I'm getting it.
Now imagine you're looking for everyone older than, say, 50.
Okay.
The histogram tells the database what percentage of people are actually older than 50.
Right, so if it's a small number, it can ignore most of the table.
Exactly. Saves a ton of time and effort.
So histograms help make those cost estimates really precise. But what if, even with all this optimization, the database picks like a not-so-great plan? Do we just have to live with it?
Not necessarily. Sometimes you know more about your data than the database does, and that's where plan hints come in.
Plan hints, so like giving the database a little suggestion.
You got it. It's like saying, hey, use this index or join these tables in this order.
Okay, I see.
But you have to use them carefully.
Oh, why is that?
Because plan hints can actually override the database's own optimization decisions.
So it's like a powerful tool that can backfire.
Precisely. If you're not careful, you could end up with a slower plan than the database would have chosen on its own.
That doesn't sound good. So plan hints, powerful, but tricky.
Exactly. It's like playing with fire a little bit.
This is all really fascinating. We've covered how databases estimate costs, how indexes and histograms help, and even how we can try to influence the database with these plan hints.
It's all about understanding those costs and how to minimize them.
Right. And before we go any further, I just want to remind our listeners to please like, share, and subscribe to The Deep Dive for more of these insightful explorations. We're going to dive even deeper the next part, so stick around.
And while you're waiting, think about this. Could there be times when a slightly slower query is actually a better choice? We'll get into that and much more when we come back.
Welcome back to The Deep Dive. We're continuing our exploration of query optimization, all of that behind-the-scenes stuff that makes our databases run smoothly.
It's a fascinating area, really.
In the last part, we talked about indexes and histograms, but earlier you mentioned this join monster.
Yeah.
What exactly makes joins so tricky when we're trying to optimize queries?
Well, joins are essential when we want to combine data from different tables, right?
Right.
But they can be, really resource intensive, especially with large tables. The database has to figure out the most efficient way to connect those tables and get the data we need.
So it's like a logistical puzzle.
In a way, yeah. The order you in the tables in makes a big difference in performance.
Oh, really?
The database has to try different join orders, looking for the one that minimizes the cost, the overall cost.
Okay.
And that's where selectivity comes in again.
Oh, right. Selectivity. We talked about that with histograms. It's about how many rows actually pass through a filter.
Right, exactly. But with joins, selectivity helps the database estimate how many rows will match up.
I see. Okay.
Imagine joining two tables based on a column that's a primary key in one table and a foreign key in the other.
Like matching a product ID from orders to a specific product.
Exactly. The database knows each foreign key matches exactly one primary key.
Okay, so because of that relationship, the database can estimate how many rows the join will produce, right?
Precisely. It knows the join won't create a massive number of rows.
That makes sense.
Yeah.
But what about joins based on columns that aren't keys?
That's where it gets a bit harder. It's more difficult for the database to predict how many rows are going to match.
And that could impact performance.
It could, because it might end up processing a lot more rows than expected.
So it's like the database is kind of guessing.
In a sense, yeah. It might have to use more complex, time-consuming techniques to estimate the selectivity of those joins, and even then it might not be perfect.
Wow. So it really is a balancing act for the database to figure out the best join order and the selectivity.
It really is.
It's pretty amazing how much is going on just to get those query results.
And it's all happening in milliseconds.
Right. And, in today's world where everything is data-driven, a slow query, that can lead to, well, all sorts of problems, can't it?
Absolutely. Delays, frustrated users, even missed opportunities. That's why this stuff is so important for anyone who works with databases.
This deep dive is really showing just how important query optimization is. I mean, we've gone from like the basics of how databases estimate costs to understanding indexes and histograms, and now we're tackling this join monster. It's like we're putting together a whole toolkit for writing better queries.
That's a great way to think about it.
But before we wrap up this part, I want to remind our listeners to like, share, and subscribe to the deep dive for more deep dives like this one.
And as we move on to the final part of our deep dive, here's something to think about. Is there ever a reason to choose a less optimal query plan? One that might be a bit slower. We'll dig into that and wrap things up when we return.
Welcome back to the deep dive. We've been on this incredible journey, haven't we, exploring all the ins and outs of query optimization.
We've covered a lot of ground.
From cost-based optimization and indexes to those tricky joins. And at the end of the last part, you left us with a question, a real head-scratcher. You asked if there could ever be a time when a less optimal query plan, one that might be a bit slower, could actually be the better choice. It sounds a little counterintuitive, doesn't it?
It might, yeah. But there are definitely situations where just going for pure speed isn't the best approach. Remember, query optimization, it's all about finding the right balance, for the specific situation. It's not just about getting the fastest time, like racing against a clock.
So it's about seeing the bigger picture, the overall goals of the system.
Exactly. Think about this. You've got a query that runs a lot, maybe as part of a batch job, and you've spent all this time optimizing it for speed, making it super fast. But during those peak hours, that really optimized query, it could actually put a lot of strain on the server.
It's like having a super fast sports car stuck in rush hour traffic.
Perfect analogy. All that power, but it can't go anywhere. So in that situation, it might actually be better to de-optimize the query a little bit, just to reduce how many resources it uses during those peak times.
So it might run a bit slower, but it won't bog down the whole system.
Exactly. Sometimes a little compromise on speed can actually help the overall performance.
So are there other times when a slower query might be the way to go?
Oh, yeah, absolutely. Sometimes a simpler query plan, even if it's a bit less efficient, it's just easier to understand, easier to maintain.
Makes sense.
And that's really important, especially when you've got a lot of developers working on the same code. A really complex, highly optimized query, that could be a nightmare for someone else to try to understand and modify.
Yeah.
And that increases the risk of errors.
Right.
It's like choosing a recipe, right? Sometimes a simple recipe, even if it takes a little longer, it's just better than some complicated one that's easy to mess up.
Yeah, keep it simple. So simplicity and maintainability, those are important factors too.
Absolutely. And sometimes they're even more important than just squeezing out every last millisecond of performance.
This deep dive has really changed how I think about query optimization. It's not just about, going fast. It's about making smart decisions based on what the application actually needs.
That's it. It's a multifaceted skill, You have to understand how databases work, how the data is structured, how all these different techniques play together. There's no one perfect solution. It all depends.
We've learned so much in this episode. We talked about cost-based optimization, indexes, histograms, those join monsters, even those tricky plan hints. It's clear that query optimization is a must-have skill for anyone working with databases.
It's a foundational skill, whether you're just starting out or you've been working with databases for years.
And it feels like we've only scratched the surface here.
We have. There's so much more to explore, a whole world of advanced optimization techniques.
Well, this has been an amazing deep dive into the world of query optimization. I think we've taken some really complex ideas and made them a little easier to understand. And hopefully, our listeners are feeling a lot more confident about writing efficient queries now.
That's the goal.
And as always, thank you so much for joining us on the Deep Dive. If you enjoyed this episode, please hit that like button, share it with your friends, and subscribe to the channel for more deep dives into the fascinating world of tech and data. Until next time, happy querying.